hard. If G is empty, then here's delta is 0. If it's not empty, then if it's not empty, then the maximum degree is at least 1. And if E prime, the H set E prime, is set such that the maximum degree of G minus E prime is just the maximum degree of G minus 1, then we consider a vertex of this set V prime, and this vertex must be incident to at least one edge of this set E prime. And at most, alpha prime of G induced by V delta edges from E prime connect two vertices, each from the set V delta, such that all these vertices are distinct. The end vertices of these edges are distinct, because alpha prime is an independence number. And for the remaining vertices, you need one additional edge from E prime each. And if you add these two values, then you see that is delta of G is greater or equal to alpha prime. This comes from here. And the remaining set, the remaining vertices is this, plus V delta, cardinality of V delta minus 2 alpha prime. And this gives this expression from the statement of the lemma. This is a one direction, it's a lower bound. And to see that this is also an upper bound, you just select an appropriate maximum matching in G induced by V delta and an incident edge for each not matched vertex from V delta. Yeah, next and last example for the edge for an edge stability number in this first part of the talk is the edge connectivity lambda of G, which is the minimum number of edges whose deletion results in a non-connected graph, or in the trivial graph, which consists just of just a vertex. We also call such a vertex a singleton. And the result is also easy to prove, is lambda of G is 1 if G is connected and not a singleton, and it's the size of the graph otherwise. If G is connected and not a singleton, then let E prime be an edge set of lambda of G edges, such that G minus this edge set is disconnected, and for each edge of these set E prime, small e, we have that lambda of G minus E is lambda of G minus 1, and this means the lambda edge stability of G is 1 in this case, and the other case is again trivial. If G is disconnected or singleton, then lambda of G is 0, and the invariant cannot be changed by edge deletions. So by definition, AS lambda of G is the size of G. So yeah, let me say something about the history of this problem. Up to now, there are not so many papers of this topic. As far as I know, the first paper on this topic was by Bauer-Harari and others, who called this invariant roll line stability number, and they gave some few results. And later on, there were two early papers of Staten, 1980, and of Professor Arumugam and others, who considered this invariant with respect to the chromatic number. So they considered the chi edge stability number. For The domination number, this problem is well studied since the so-called bondage number, B of G, is the gamma is the domination number, is the gamma edge stability number of the graph. And there are a lot of papers for this parameter. So next I will give some general results on this invariant rho, E is rho of G. So if I will start with an upper bound. Let H be a spanning subgraph of G obtained from G by removing K edges. Then the rho H stability number of H plus K is an upper bound of the rho H stability number of G. And if rho of G and rho of H differ, then even K is an upper bound. So next, I will consider rho of G with some additional property. First, if rho of G is additive, and then let G be the disjoint union of K subgraphs H1 up to HK, and the integer S is defined such, or we arrange the indices in this way, such that rho of HI can be changed by H deletion if and only if I is less or equal to S. And the result is then if rho of G is the size of the graph, if F is 0, and otherwise is rho of G is the minimum of all the is rho of G of HI, and I is less or equal to S. So we need only to consider the first S of these subgraphs. And for maxing and monotone increasing invariance rho of G, we can prove with the same, if G is again the disjoint union of H1 up to HK, and again the indices are arranged such that rho of HI is equal to rho of G if and only if I is less or equal to S, and then the result is equal, yeah, and then as rho of G is the size of the graph if there is a subgraph Hj such that rho of Hj cannot be changed, and otherwise as rho of G is the sum of these first S rho of Hi, as rho of Hi. Now you see again we arrange the subsets H1 and HK in a special way like this, and we get this result. Yeah, what does it mean? That means that you can, in these two cases, when rho of H is additive or when it is maxing and monotone increasing, then you can compute the rho H stability number of G by the rho H stability number of its subgraphs, of its disjoint subgraphs. That means we can consider without loss of generality in the following that G in these two cases, that G is a connected graph. So for monotone graphs, I will give a lower bound. We have already had an upper bound. Here's a lower bound. If rho from G is monotone, but the upper bound was in general, this is only for monotone invariance. If rho of G is monotone and G is a non-empty graph with the value of rho is K, and if G contains S non-empty subgraphs, G1 up to GS, such that they have the same value of the invariant like G itself, namely K, and A is defined to be the number of edges that occur in at least two of these subgraphs. And Q is the maximum number of these subgraphs with a common edge. And then we have two lower bounds. First one is rho of G is greater or equal to S over Q. And second one is rho of G is greater or equal to the sum of A is rho of GI for I from 1 to S minus this factor A times Q minus 1. So in this case, we do not need that these subgraphs G1 up to GS are different. They can be the same in this case. And we get as a corollary, if we choose Q to be 1, that the following result, let rho of G be monotone and G be a non-empty graph. This rho of G is K, and G contains S non-empty subgraphs, G1 up to GS, with the same value of the invariant as G, and pairwise disjoint edge sets, then S, this S is a lower bound for the rho edge stability number of G. And if we choose S to be 1, then we get this result. If rho of G is monotone and H is a subgraph of G with a property that rho of H is equal, coincides with rho of G, then A is rho of G is less or equal to A is rho of H is less or equal to A is rho of G. Note that in general, A is rho of G must not be monotone, even if rho of G is monotone. So, but if rho of H and rho of G coincides, then we have this monotonicity. Yeah, let me continue with the result, which is a little bit similar to a result, to a well-known result of this one. Maybe you all know it. Alpha of G plus beta of G is N of G. This is the result of Galli. He proved it at the end of the 50s in 1959. And the result says that alpha of G plus beta of G is N from G, and alpha of G is the independence number of the graph, beta of G is the vertex covering number of the graph, and N of G is the order of the graph, the number of vertices. And alpha of G, the independence number, is defined as, maybe all of you know, as the maximum number of mutually non-adjacent vertices of G, and beta of G is the minimum number of vertices of G, such that every edge of G is incident to at least one of these vertices. And we proved a result which is similar to that with two invariants which are based on the edge stability. And these two invariants are the following. Here's the definition. If rho of G is an invariant, then let alpha rho prime of G be defined to be the maximum number of edges of a spanning subgraph H of G with a different value of the invariant, with rho of H unequal to rho of G. And if such a subgraph does not exist, that is, if rho of G is constant for all subgraphs, for all spanning subgraphs of H of G, then we set alpha rho prime of G to be the size of the graph. And beta rho prime is defined to be the minimum number of edges that cover all non-empty spanning subgraphs with the same value of rho, namely rho of H is equal to rho of J. That is, each subgraph, the cover, means that each subgraph must contain at least one edge of the covering set. And with these two invariants, alpha rho prime and beta rho prime, we could prove this result if rho of H is not constant for all spanning subgraphs H of V. That means by deleting edges, once you can lower the value of rho. You can not lower, you can change it. Then is rho of G is the size of the graph minus alpha rho prime. This is a general result. And if we have in addition that rho of G is monotone, but not constant with respect to spanning subgraphs, then this equation holds, namely alpha rho prime of G plus beta rho prime of G is M of G, the size of the graph. And if we put together these two results, then we get this corollary. If rho of G is monotone but not constant with respect to spanning subgraphs, then is rho of G is just beta rho prime of G. That means instead of determining is rho of G, we can try to determine beta rho prime of G in this case when rho of G is monotone but not constant. Okay, then in the next step of my talk, I would consider special invariants. So I will start with the invariant chromatic number we have already defined at the beginning. So let me say that instead of chi-H stability number, we also use the notation chromatic H stability number in the following. And since the invariant chi of G is monotone increasing, then we can apply these two general lower bounds, which I mentioned before. And these lower bounds sounds as follows for the chromatic number chi of G. Let me repeat. Let G be a graph with chromatic number chi of G at least 2, and the G contains S non-empty subgraphs G1 up to Gs. Once more, it's not necessary that they are different, with the property that they have the same value of chi as G itself, namely K, and such that A is the number of edges that occur in at least 2 of these subgraphs, and Q is the maximum number of these subgraphs with a common edge. Then both inequalities hold, namely as rho of G is greater or equal to S over Q, and as rho of G is also greater or equal to this expression over there. Okay, and again, when we choose the case Q to equal to V1, so that mean any such edges in just in at most one of the subgraphs GI, then we have this result. Let G be a graph with chromatic number K, and if G contains S subgraphs, G1 up to Gs with the same chromatic number and pairwise disjoint edge sets, then S, the number of these subgraphs with the same chromatic number, is a lower bound for the chi edge stability number for the chromatic edge stability number. And if we choose S to be 1, then we get this corollary again. Next, I want to consider the union of two graphs. And we define the union such that the edge set is such that the two graphs G and H must not necessarily be distant. Yeah, this is important to know for the following. And we prove this result if G and H are disjoint or they have exactly one vertex in common. Then we can determine the chromatic edge stability number of G union H. It is the chromatic edge stability number of G if chi of G is greater than chi of H, it is the edge stability number, the chi edge stability number of H. If chi of H is greater than chi of G, and it is the sum of both if the chromatic numbers of H and G coincide. And if we apply this theorem several times, then we get this result. If let G be a graph with B blocks, B1 up to BB, such that chi of BI is chi of G for the first S of these blocks, namely for B1 up to BS, and chi of BI is less than chi of G for the other blocks, then the chromatic edge stability number of G is just the chromatic edge stability number of the sum of the chromatic edge stability numbers of the blocks for which have the same chromatic number as G. The other one do not play a role. So what does it mean? That means that in considering or in trying to determine the chromatic edge stability number of a graph, we can assume in the following, without loss of generality, that the graph is two connected.
Can you give some examples?
Examples will come. Yeah. Okay. Yeah. Next result is for the join of two graphs. If G and H, if G join H is if we consider the join of the graph, and this is a definition, maybe all of you know this. The join of two disjoint graphs G and H is a graph composed by a copy of G and a copy of H, and each vertex of G is connected by an edge to each vertex of H. And let T of G be the minimum number of vertices in a color class of the graph, where the minimum is taken over all chi colorings of G. And then we have this result. We have an upper bound for the chromatic edge stability number of the join of the graphs G and H. Namely, it is the minimum of these three expressions. E is chi prime. It's defined, you see in the first line of the theorem. E is chi prime of H, and the product T of G times T of H. And last, we conjecture that this is not only an upper bound. We conjecture that this is an equation every time in the statement, but up to now we couldn't prove it. And last, let me give this result. Let me tell you what is the result for Cartesian product. The Cartesian product of two graphs is a graph with vertex set Vj times Vh, two vertices Ui, Vi, and U2, V2 are adjacent, even only if U1 is U2, and V1, V2 is an edge of H, or vice versa, if V1 is equal to V2 and U1, U2 is an edge of G. And then it implies this. And the max, and note that the chromatic number of the Cartesian product of G and H is just the maximum of chi of G and chi of H. And we could prove this result. The chromatic edge stability number of the Cartesian product of G and H is the number of vertices of H times is chi of G and so on. You can see this. And in case that chi of G and chi of H coincide, then we have the sum of these two expressions before. Yeah, now here are the examples. Here are the examples you asked for. With applying these general results on the chromatic edge stability number, we could determine the chromatic edge stability number of some well-known classes of graphs. Here are some examples. The first three are the introductory results I already mentioned at the beginning. And for example, for complete multipartite graphs, the chromatic edge stability number is N1 and N2. What does it mean? Yeah, if you order the indices of the complete multipartite graphs you see in this way, then N1 and N2 are those components with a minimum number of vertices. And this is the result, which was open for a while. And also we could determine, this is easy, the edge stability number, the chromatic edge stability number for wheels, yeah, which wheel WN is just a join, and with this result for joins, we could determine this also for fans, for cactus graphs, with as odd cycles. In a cactus graph, each edge is at most in one cycle, and for some other classes of graphs, we determined the chromatic edge stability number. Yeah, and let me next come to another invariant. Next and least, my least example is a chromatic edge. Is a chromatic index of the graph. We already defined this, chi prime of G, and by the result of Wiesing, who proved that maximum degree +1 is an upper bound for the chromatic index, and by the trivial bound delta of G, with a trivial lower bound delta of G, we know that we have only two possibilities for chi prime, namely delta and delta +1. Delta, these are the class 1 graphs, and delta +1 are the class 2 graphs. And with this, we define the invariant class of G in this way, namely chi prime minus delta +1, which is 1 or 2. And again, instead of chi prime edge stability number, we will use the notation chromatic edge stability index. And this is an upper bound for if chi prime of G, namely it is less or equal to alpha prime of G. And if G is non-empty and the trivial case G is empty, then it is 0. So we proved the lower bound. This was an upper bound. Here's a lower bound for class 1 graph. The chromatic edge stability index of G is lower bounded by is delta of G. I just defined the class delta is delta of G. And if G is and we found an example, or we found graphs such that this is not only an inequality, but it is an equality. Namely, if G is a class 1 graph, which is an addition regular, then is chi prime of G is delta of G. And in a sense, we could classify all graphs such that this equality holds. Namely, if G is a class 1 graph, then it holds that is chi prime of G is equal to is delta if and only if G is empty, or if there is an edge set E prime with cardinality is delta of G, and delta of G minus E prime is less than delta of G, and G minus E prime is in class 1. So and another result in this context is that for the first result was for class 1 graphs. Here we have class 2 graphs. If G is a class 2 graph, then the chromatic edge stability index is the minimum of is delta of G and is class of G. So if you compare this with the first result, then you see in this case, we have that is delta of G is a lower bound for the chromatic edge stability index. And here we have that this is an upper bound. So this, you see, these two invariants, the chromatic edge stability index and class of G are very close connected. So yeah, using these results I just presented to you, we could again determine the chromatic edge stability index for some classes of graphs, and among others, here you can see some of the results. The chromatic edge stability index of a complete graph is n/2 or n-1/2, depending whether n is even or odd. For bipartite graphs, is chi prime of G is the same as delta of G. As delta of G, I determined at the beginning of my talk, so we know the value of AS delta of G. For complete bipartite graphs, for paths, and for cycles, and for wheels, and for some other classes of graphs. But I think these are enough results for this talk, and therefore I would conclude with some references to this topic, and I thank you very much for your attention.
Are there any questions? Well then. If there are no any questions, then
No, I'm asking one question. So, these results are regarding stability number with respect to chromatic number. So, how about stability number with respect to domination number? And has it been studied with respect to domination?
Yes, that was what I told when I gave some information about the history for domination numbers. This is well studied. There are very lot of papers for the domination number.
Yes.
There's wide results.
Yeah.
For the domination number,
Yes.
because I said there was this coincidence between these two parameters, between this stability number and this B of G of
Yes.
for the
But seems to be very
domination
interesting,
number.
very interesting topic.
Thank you.
And I think for the researchers, we can give this problem that characterize graphs for which stability number with respect to domination is 1.
Yeah, okay, for example.
Yeah.
And I think it's a nice question for everybody. Take any
Yes.
invariant,
Any number.
any invariant you like, and then try to
Yes.
determine the stability number with respect to this invariant.
Yes.
So I have given at the beginning 3 easy examples: minimum degree, maximum degree, but take any other one and try to determine
Yeah.
the stability number.
Yes. Some good results can come. Yes. Thank you.
Any other questions? Let's thank Professor Chemnitz again.
So our next speaker is Professor Kiki Arianti Sugeng, who is a faculty at the Department of Mathematics, Faculty of Mathematics and Natural Sciences, University of Indonesia. Her PhD is from the University of Ballarat. She worked under the guidance of Mirka Miller and Martin Bacha. And the title of her thesis is Magic and Anti-Magic Labeling of Graphs, a topic in which she has been very active ever since. She took part in a World Bank funded project, Quality of Undergraduate for Education. From 2013 to 2017, she served as a chair of the MKI, and she's still active in that organization. She published over 155 publications, which has over 900 citations. And she's very active in different topics of graph theory. She has taken part in projects on the topics of metrics, dimensions of graphs, graph labeling, magic labeling, and rainbow connection. On a personal note, we have just discovered that we actually have a joint student. One of my recent graduated Indonesian student, Inga Sini, was her student earlier. Please welcome Professor Sugeng.
Okay, good morning, everyone. So thank you very much for the introduction, Professor Eva. I would like to thank the organizer to invite me to this nice conference, and also I have the opportunity to visit New Delhi University and also New Delhi. This is the first time I came to New Delhi. So today I would like to share like one of my research on modular irregularity strength of several families of graphs. So before Professor Chemnitz already mentioned about the invariant of the graph. So might be this is also like one of the kind of invariant graph, and we can combine like the two of the perfection. So might be we can also continue to find the stability of this invariant of the graph. Okay. So I'm from Universitas Indonesia, and also I involved with the collaboration research with other universities in Indonesia. So what's happened with? Okay, we need to wait for the technical program. Yeah. So the modular irregularity strength is the modification of the irregularity strength that is already introduced before. So Can we change it to? Okay. Okay, so the outline is a short introduction and then the non-result. I didn't put like all non-result because this is like what is starting to blooming. So there are like many results, like new results coming. And I will tell about our result on some families of graph and conclusion, sorry. So the idea is come from the irregularity graph. So we have usually we knows about regular graph, right? So the question if there is there any graph that has irregular in the meaning of the degree of all vertices are different. And the answer for the simple graph, we cannot have it. But for multi-graph, we can have it like the example here. So if we have this multi-graph, then we can calculate the degree. This one, the degree is 2, this one is 3, this vertex is 5, and this is 4. And we can have a multi-graph with all vertices has degree all different. And with this idea, we can like change the number of the edges here. So like in this part, we can like put the label 2 in here, means that there are 2 edges between these 2 vertices. This we can label it 1, and this one we can label it 3, and this is 1. So this is the idea of the irregular labeling. So we label all the edges such that all the degree or the sum of the labels are different. So the SK labeling and also irregularity labeling introduced by Chartran et al. In 1988. So we have the SK labeling. So we have label all the edges with number 1 until k, and we calculate the vertex of the sum. So the weight of the vertex is the number, the sum of all the labels that incidence to that vertex. And the numbers or the vertex sum or the weight can be between 1 until some numbers here. So it's a positive number. The irregular labeling is defined as the labeling, the K labeling like I mentioned before. So this is the label for all the edges to 1 until K with the weight of the vertex X is equal the label, it should be Fxy here. So the sum of all the label of the edges that incidence to this X. And we want to make sure that all the weights are different because this is the generalization of the irregular graph with the multi-graph, the number of edges. And we try to find the minimum number of K such that this kind of labeling exists, and the minimum K will call irregularity strength. So when we come back to the previous example. So this labeling is 1, this is 1, this is 2, and this is 3. So the minimum label for the minimum of the maximum label here is k. K is equal to 3. So the strength is equal to 3. Okay. So Bacha et al. In 2020 defined the modification of the irregular labeling. So previously, irregular labeling has many variations like vertex irregular labeling, edge irregularity labeling, total, reflexive, and many of the variations. So this is one variation that introduced recently in 2020. The difference between the modular irregular labeling and the irregular labeling is in the modular part. So the weight will be calculated based on the modulo. So the what is the codomain will be the Zn. Yeah. Okay, so the two vertices is different. Yeah, the weight. And the smallest positive integer, we call it modular strength. So the difference between the irregular labeling and the modular is in here. So in irregular labeling, we just add all the labels of the edges incidence to the vertex. In the modular, we calculate this one with the modular of the n. Yeah. So because of this difference, so if we can find the irregular labeling that is consecutive, say it's 3, 4, 5, 6, 7, and so on, and then we put it in modular, so we can have 0, 1, 2, 3 until n. Yeah. So it means that if we have a consecutive weight for this kind of regular, that is automatically modular irregularity strength, modular irregularity labeling. Sorry. So this is the example. On the left-hand side, we have the irregular labeling. So we label 1, 1, 2, 3 like the previous example, and we have here one. So this is should be 5. So this is 2, 3, 4, 5, and then if we make it as a modular, because we have n equal to 4, then the 5 here change to the 1. Yeah, and the 4 change to the 0. So we have n equal to 4. So we have 0, 1, 2, and 3. Yeah, this one should be 5 here. So this is the irregular one, consecutive, and we can change it by the modular. Then we have modular irregular labeling, and also the strength will be the same. This is 3, and this is also 3. But we know that in irregular labeling, sometimes we can like have different label here. So like here we have non-consecutive integers. So we have weight is 3, 4, 5, 6, and then 8. So we miss 7 in here. So we cannot take this label to be a modular automatically, but we have to relabel all the label of the edges, maybe not all, so that we can have, so here like 2, 2, we can change it with 1, 2, this 3 still keep 3 in here, 1, 3 change to 2, 4, and then this is 2 change to 3. With this new labeling, we have a modular irregular labeling. Yeah, we can calculate this one. So 2 and 3 is equal to 0 because we have 5 vertices in here. 1, 3, 2, this is 6. So modular 5 will be equal to 1. 1 plus 2 is 3. 2 plus 3 and plus 4 is equal to 4. 4 plus 3 is equal to 2. And we will have 0, 1, 2, 3, and 4. Yeah, so this is the example of the irregular labeling that not the same with the modular irregular labeling. Yeah. So how if like we still keep this one? Can we have the irregular labeling? So we can see that if we calculate it as without the modular, we can have 3 in here. We have 6 in here. Okay, we have 5 in here. This is 7. This is 9. Yeah. So we will have, wait a minute. Yeah, sometimes we can put the same what is the same so irregular labeling that is consecutive automatically modular irregular. Modular irregular if it's always consecutive, but not always be irregular labeling. So it's not like what is one-to-one correspondence in that. So this is the example of the non-consecutive base. So we will have 0 in here. So if we calculate this one is this is 5 plus 4 plus 2 plus 4, it will be so my mathematics is like not working at this time. Okay, but we if we calculate this is can be 0, 1, and then this is 2, 3, 4, and so on. Yeah. But if we calculate it like one by one, we can see there are some of the label are the same if we not calculate it as a modular. Okay, so let we see what is the null result. So from the first paper, Bacha already found the modular strength for path, star, triangular ladder, cycle, and gear graph. And then Mutuguru Pakiam et al. Found the tadpole and double cycle graph. In 2021, Bacha et al. Found the fun graph. Me and my students, and we have regular double star and friendship graph. And this is with Andrea. They found the wheel graph. So this is like the several non-result that are in this area. For the lower bound, for the irregular labeling, Catherine already mentioned. So this is the maximum of like pi min 1 over I plus 1, where pi is the number of vertices with degree I. Yeah. And for the regular graph, the deregular, the lower bound is like simpler, and it's from the observation we know that the modular strength of the graph should be greater or less of the irregular strength. And also in their paper, Bacha et al. Found that if the number of vertices is 2 modulo 4, then we cannot find the what is the MS of this graph, and the modular strength will be denoted as infinity. So we can see that the weight of the vertices, that is the strength of the graph, yeah, the K, so can be infinity. Yeah. This is for sure for 2 modulo 4, but it might be also found for the other number of vertices. So we start with our result. Because in India we can find lots of flowers like here. So I started with the family of graph, flower graph. So the first one we call it rose graph. Actually, it's not really a rose graph. This is the example of the graph. This is what you call it, the middle of cycle or something like that. So the MSN. So it has it comes from the cycle, and so this is like the cycle. So when we have the cycle, for the edges we put like 1 edge and then connecting So we can have a graph like this. But actually, if we only see the what is the graph, yeah, the picture, without thinking about the middle graph, so this is come from the cycle and then like put like some leaves on the every edge. Okay, so this is with the also with Andrea. We have a paper that is already accepted. Hopefully will be published in this March or April. And we can see that the rose graph will be the modular strength will be n over 2 plus 1 for n even. And for n odd, it will be the number of edges, the number of vertices will be 2 modulo 4. So this is the infinite. So how we prove this kind of construction? So first, we define we define the lower bound. Yeah. So for the n odd, we have the modular strength is equal to infinity. So we can like skip the what is the case. For n even, from the lower bound that the modular strength will be greater than strength. So we can have n over 2 plus 1. And then the next step, we have to find the upper bound. So to find the upper bound, it means that we construct the label of the graph. If the upper bound equal to the lower bound, then it means that we are lucky because we can have the modular strength. But if we have the construction is greater than the lower bound, so we have two possibilities. One is proof that we cannot reduce the upper bound. And the second one is try to find the other construction that might be have a lower upper bound. Yeah. So for this one, we construct the label like this. So this is the label for every edges inside the cycle. This is for the AEB, this one AIBI and AI plus 1 BI. It means the edge on the like the what you call it, the for the flower leaf and so on. And then we show that this has n over 2 plus 1 labeling. So the k will be n over 2 plus 1. Because for this construction, we have the maximum label we use is n over 2 plus 1. This is the same as the lower bound. So we are lucky here. And the last one, we have to prove that the weight of vertices are different and constitute the set of that 2n. Yeah, if we finish this process, it means that we already finished all the proof. In this case, we are lucky because we have the construction, the k is equal to the lower bound. So it's finished. Okay. So this is the example. Inside the cycle, we label all with 4. So 4 is the maximum. Yeah, the k. The k is equal to 5. So we put 4 in here. And if you can see what is the pattern? So we have 1 1 here, 1 2 2 3 3 4 4 5, and then what is we from 1 1 we have on the right hand side we have 2 2 3 3 and 4 4. So it looks like we have pattern that have symmetric. So on the right hand side we have like 1 1 1 1 2 2 3 3 4 4 until half of them, and then here we have 1 2 2 3 3 4 4 5, right? And all inside will be all 4. So we can calculate the weight, and we can have like 0 in here until 15, I think. Yeah, until 15, because we have 16 vertices in here. So because the patterns after several several months try to figure out, because this is manually, not using the computer. And we see that the label is quite easy. We continue with the others. So we are thinking, because in the middle, this is cycle, how about in the middle, we put the complete graph. So we have a daisy graph. Yeah, so we put like additional 8. We know if we put additional 8, what happened, and if we reduce the 8, what we will have. Okay, so we have the similar modular strength for this one. This is the example, because like for this construction, we just like put all 1 in here. Yeah. But if you remember, this is previously will be like 4, like for every edges. But because we have additional 3 edges inside the cycle, so we can reduce the number for here, but it cannot be like 1, 1, 1, but it's 1, 2, 1, 2, 1, and 2. So we have the same weight in here. And we can see the construction will be the same on the outside. So this is 1, 1, 1, 2, 2, 3, and 3, 4. And this is 2, 2, and 3, 3. Yeah, it's similar. Like there is a pattern in half on the right-hand side and left-hand side, if you can see it like that. Okay. So the last flower is sunflower graph. The sunflower graph we put in the middle is a wheel. So we have cycle, we have complete, and we have wheel in here. We have almost the same. So this is, sorry, I will be back. Yeah. So we have n over 2 plus 1 here for the rows graph and also the daisy graph. And here we have also n plus 1 over 2, but for the several cases like n equal to 3 and n equal to 5, we have a different number. Yeah, so sometimes on the what is the smaller number of vertices, we have a different pattern. Okay, so this is the example of the graph. We can see that the complicated complicated label is how to deal with the center in here. For the other will be the same, yeah. Okay. The next one, we would like to share the result with the regular graph. We have project with some of other colleagues for the dodecahedral graph, and we try to find the label of the generalized one. So this is the example. So this is the dodecahedral graph that we already know, and we try to find the generalization like this. So this is like a prism, but we add like more edges in here with distance 2. Okay. So this paper already published with some of colleagues in here, and we have the modular strength is 2n plus 2 over 5 with the scaling for an even and for an odd. We know that it's equal to, or it's 2 modulo 4, so it will be infinite. So this is the construction, yeah, the example. We can see the pattern like here 1 1, and this 2 2, 3 3, 4 4, 5 5, 6 6, and we have problem in here because there is like a different pattern for every number of graph. And the inside will be 2 2 3 3 4 4 5 5 and so on. And this is 7 7, but it's not always like this. Yeah. And also for the rim, we have 1, 1, 1, 1, 1 here, and 2, 2, 2, 2 here, and 2, 3, 3, and then we have to find what is inside here. So there is some swapping of the label in here. But inside we can see all the additional edges. We put it 7 all in here. So the modular strength will be 7. So because this is like the modification of the prism. So we think that if we delete all the additional edge in here, then we can have prism, and then we can have the nice result, and we can find the MS of this graph easily. But actually that is not that case. So we have to like find some of the modification of the label. So we cannot like just delete all the 7 and then we can have 6, something like that. So this is the modular strength. I give you the very simple example. This is the smaller one, and we can see all in here we have 1, 1, 1. So it's not like really show the pattern, like half something like that and half the other. And we have like 3, 3, 4, 1 in here, but we can see that the weight will be like 0 in here, 1 in here, 2 in here, 3 on the outside, 4 the outside, 5 the outside, 6 the outside, but 7 coming back inside. So the pattern a little bit different with the dodecahedral previously. Okay. From here, we try to find the ladder. Yeah, because the ladder is just delete the 2 parallel edges in here. But unfortunately, we still not lucky enough to get the pattern. So we have the lower bound and we have upper bound, but we still cannot choose which one is the exact modular strength for the ladder. So we are still working on it. But the Mobius ladder, the pattern is look more complicated than the ladder, but we can have the exact value for the modular strength here. Okay. This is the example. So we can see there is also like some kind of pattern except in this box. So in this box, we have to like swap the pattern from the previous one, the prism. And we cannot like just delete this one to get the ladder. Yeah, it's easy to see after we get the label, but for finding this what is this pattern, we have to spend like some time to get the right pattern for all the cases. Okay. So until now we have like a kind of family of flowers. This is like the this 2 is the regular graph, have family with prism graph. We still have like some more results that inspire us to like do the future results. So the open problem is find the characteristics graph that has non-consecutive labeling, that is not like automatically irregular and modular irregular labeling, because some of the results we can like see the both labeling are the same, and characteristics the graph that has constant modular irregularity strength, because we know that the complete graph has a modular strength equal to 3, and then the complete graph minus all the matching, we have the modular strength is equal to 4. but we still haven't got more results with the constant. So we still looking for what is the characterization that the graph can be a constant modular irregularity strength. And also we can try another families of graph and try to find the modular irregularity strength for them. And right now we are looking for the product. So if we know the original graph and then say like right now with my student, I work in the union of the like cycle. What is? I think we already try like 3 different family of graph, and then we find the union. Some of them we can find that the say that we have the union of K graph, K cycle. So the modular strength will be the K times modular strength of the graph. That is for the copies, yeah. But for like a graph that has center, like the sunflower, we cannot find the pattern of the union. Yeah, but we just started like several months ago, so this is on progress. And also we can see that like the prism is the cross product from CN and P2, and we can also like try to find the general prism or any other product of the graph. So here is the references that we have. Okay. So Bacha and general, the modular irregularity strength of graph is introduced by Bacha, Katrisan, Mutuguru Pakiam, and Ramya. So the 3 of them are from India. And there is like more result in this graph. So this is also like the result for the modular irregularity, and this is like our result that will be published in this month, hopefully. So thank you very much for your attention. Thank you, Professor, again. Are there any questions? You need this one? Well, let's thank Professor again.
Now I'd like to invite Professor Andrea to
Yeah.
felicitate.
Professor
Yeah,
Eva.
Professor Eva to felicitate Professor Kiki with the token of memento.
Thank you.
Thank you so much. Thank you so much, man. Thank you. So, so first session of the last day of the conference is concluded here. So now we have a tea break. And one announcement is that regarding your relieving certificate, if you want, you can contact help desk. Okay, please take your form, fill it, and submit to them.
Thank you.
Okay, and any kind of queries and information if you need, please ask them. They will note it down and they will send it to us. Okay, thank you so much. Thank you. Good afternoon, everyone. So welcome again in the second session of the last day of the conference. Now, I would like to request Professor Jay Bagga to chair this session. Sir, please. Please do come, sir. Thank you, sir.
Thank you. So I'm pleased to welcome you to session 2 of this morning. And we have 2 speakers in this session. Our first speaker is Professor Laszlo Zekli, and he is currently a professor at University of South Carolina, where he's been for a while. Professor Zekli received his PhD from Etwash University back in 1983. And since then, he's been associated with many institutions, including Etwash University as an associate professor, University of New Mexico as a visiting associate professor, and also other universities, including University of Auckland. And he has been an Alexander von Humboldt Fellow at University of Bonn, among many other positions that he has held. He works in many areas of graph theory, and today he's going to speak to us on variants of biplanar crossing numbers. Professor Zekli.
First of all, I would like to thank the organizers for the generous invitation to this great conference. And the talk will be about biplanar crossing numbers. I have been working on biplanar crossing numbers in the last 20 years. So my help. So these are many papers that I will mention. In most of the papers, Eva is a collaborator, and so many other people are involved that I only mention other names at the results. So this is about
Hello.
yeah, it did not work. Thank you. Thank you. So first I have to speak about crossing numbers of graphs, since biplanar crossing numbers is a kind of a branching of the general crossing number problem. So what is a graph doing? So we have a graph, we map vertices of the graph into points of the plane and represent edges with simple curves connecting the endpoints in the plane, and curves are not supposed to pass through vertices. So if you know what is a planar graph, and all of you know that this is how planar graphs are drawn. And we pretty well understand planar graphs, but it can happen that a graph is not planar and we still want to draw it. And a graph drawing can be very messy, and visual understanding is important, and it helps if we can draw the graph with few crossings, since this is the bigger obstacle of visual understanding. So the crossing number of a graph in a drawing is, we consider pairs of edges and we count the number of internal vertices of the edges that they share and add it up for all pairs of edges. So this is the crossing number of a drawing. So the crossing number of the graph is that we consider all drawings, there are infinitely many of them, and try to find which one has the smallest crossing number. And this is the crossing number of the graph that I refer to, and I abbreviated with CR of G. So I would say that this is the standard concept of crossing number, since there are many alternative versions of the crossing number. So the crossing number problem started in World War II when Paul Turan had to work in a work camp, which was actually a brick factory. And in the brick factory, the inmates had to carry the bricks in small carts on some kind of rails from the kilns to storage areas. And there was a rail from every kiln to every storage area. And that was not a particularly hard work, but bricks tended to fall out from the little carts when the rails crossed. And Turan started to think how in an ideal world the kilns and the storage areas would be connected. And that actually the problem of crossing number of the complete bipartite graph. So ZNM is this formula for NM numbers, and this is supposed to be the crossing number of the complete bipartite graph KNM. And you actually can get this number of crossings from these drawings, where actually the edges are drawn in straight line segments. That's not required, but we are lucky to have such a drawing. And N vertices are on the vertical axis, evenly distributed between the positive and negative parts, and the M vertices are on the horizontal axis, again evenly distributed between positive and negative parts. And you may not see that this is the number of crossings in this picture. There is ugly algebra behind it, but that's it. So Carankiewicz conjectured that this is the crossing number of the complete bipartite graph. Even more, he proved it and published it in 1954. And Urbanik gave another proof in 1955. And then two smart graduate students, Ringen and Kainen, started to ask about certain details of this proof, and those details were never filled up. So actually, Guy wrote a paper with the title of The Rise and Fall of the Carankiewicz Conjecture, but this is kind of covered by some computer stuff. So I mentioned that there are many versions of the crossing number problem. Poch and Todt actually wrote a paper with the title, Which Crossing Number Is It Anyway? So the issue is that you can slightly change some parts of the definition of crossing numbers, and you would intuitively say that, sure, that's the same. And it could be the same, but nobody has a proof. So there are several versions of crossing numbers other than the standard, and it's conjectured typically that they are the same, but this is just not known. And that's kind of a messy foundation situation. So I would like to mention the book of Imre Lakatos, Proofs and Refutations, which considers two examples how mathematical thinking develops. And his two paradigmatic examples are Euler's polyhedral formula and the concept of the real function. And basically, his point is that people wanted certain kind of things, and then they twisted the definitions that we have these kind of facts. And this is not something that mathematicians are happy to acknowledge, but this is what goes on in science. So Sir Karl Popper was the greatest philosopher of science in the 20th century, and Lakatos tried to apply his ideas in mathematics. So that we have these foundational issues and multiple wrong proofs kind of very nicely supports Lakatos's argument. So Czarankiewicz' proof actually was published in textbooks. When I was a high school student, I had the Hungarian translation of Oysten Orr's graph theory textbook, and this theorem was in it, and there was a footnote from the publisher, and the publisher's reader was Professor Katona. The footnote was that this proof is wrong, and I was really shocked as a high school student. So the Harari-Hill conjecture. So Hill was an English architect and artist who became interested in the crossing number of the complete graph. And actually Hill took classes from Lakatos. That's an interesting thing. So the conjecture is that this HN number is the crossing number of the complete graph. And there are several drawings which give this number of crossings. The Supken drawing, the slope drawing, and some results of Moon and Boyan-Mohar on spherical drawings. Abrego and others proved the correctness of this formula for drawings of certain structure, and that's the most general result. Drawings of that structure are something like 0% of all drawings, but this is still something. And I would like to give a percentage. The closest way to get to this conjecture that this expression is the crossing number of the complete graph on 8 vertices is Balog, Liditsky, and Salazar, which proved 98.5% of the conjecture. So it's pretty close, but still looks hopeless. And this formula is so nasty that first it was not even discovered. So the conjecture was given separately for odd and even cases, and there was a formula for the odd case, a formula for the even case, and actually the two can be merged into this. So drawings on the sphere are equivalent to drawings on the plane through stereographic projection. So Moon's idea was to draw the complete graph Kn on the sphere, locate the points randomly, n points on the sphere, and then any 2 points determine a main circle, and then take the shorter arc of the main circle connecting the 2 points. So that's a random drawing. And Moon's observation was that if he does here, then the expected number of crossings in this drawing is 1/64 times n to the 4.
And asymptotically, this is the same as h of n. So that shows the difficulty of the conjecture, that you can asymptotically that close to some kind of zillion and random configurations. So what is the slope drawing? I show the slope drawing for K5. So actually take a regular Kn drone and rotate it in a way that no line segment is exactly horizontal or vertical. Well, that should be easy. Then do the following. Take all lines with positive slopes and all lines on negative slopes, and put the positive slopes on a hemisphere above it and the negative slopes on a hemisphere below it. And that's a spherical drawing, and it's equivalent to a planar drawing, and it has HN crossings. It's amazing, quite ugly calculation. The original construction of Hiller and Harari is the soup can drawing. So that's a soup can. So put in the soup can a straight line drawing of a regular Kn on the top, similarly on the bottom. And then on the side of this surface, connect vertices with the shortest arc with geodesics on this surface. And if you do that, that has the right number of crossings conjectured by HN. So I would like to mention the crossing lemma. The crossing lemma was discovered independently by Tom Layton and Aitai Shvatal, Newborn and Semeridi. So it says that if you have a simple graph G on n vertices and m edges, then either m is at most 4n. So which means that you are close to a planar graph. And if that's not the case, then you have this positive lower bound for the crossing number, which is cubic in the number of edges. It comes essentially from Euler's polyhedral formula, which implies that the crossing number of every graph is at least m minus 3n plus 6. Oh, well, if it has at least 3 vertices. We are not interested in graphs with less than 3 vertices. So, there was an amazing conjecture of Erdős and Richard Guy a decade before the crossing lemma, who conjectured that if the number of edges is sufficiently separated from n and n squared, so it is superlinear but subquadratic, then this fraction that the minimum crossing number of a graph with n vertices and m edges, well, divided by m cubed over n squared, which is the same as multiplying by n squared over m cubed. So that's the other side of the crossing lemma, the lower bound, that actually converges to a positive constant in this whole range. That's an amazing conjecture, since without the crossing lemma, you don't even know that this constant is positive. And it is. So, Bach, Spencer, and Toth proved the existence of this limit, and this is called the mid-range crossing constant. And actually, they made a remark that this constant also exists if we modify the concept of drawing and we allow drawings only in straight line segments. And that's a big success of the probabilistic method. It's a pretty complicated proof. So what do we know about the mid-range crossing number? So it's at least 1 over 29, but Bach, Radojcic, Toth, and others had a drawing which proves that the ordinary and both the rectilinear mid-range crossing constant is at most this number. And it's completely unknown where is it between these two bounds. And Bach and others' construction is basically the same. Consider a square grid. And then in this square grid, connect two vertices if they are closer to each other by a number d. And you can vary this parameter d. The number of edges in the graph depends on this d. Now, the problem is that if you make a straight line, it contains lattice points. So therefore, perturb the points a little, randomly, infinitesimally small. And then you get this constant as the number of points or the size of the grid goes to infinity. So finally, I arrived at the topic of the talk, k-planar and biplanar crossing numbers. Owens in 1971 introduced the concept of biplanar crossing number. And it has electrical engineering motivation. So the biplanar crossing number would be basically a plate, and you have certain devices in it which go through the plate, and you can make connections on the upper side and connections on the lower side. And you still want to minimize crossings of wires, since if there is a crossing, there is an increased likelihood of interference of the electronic signals. So how to minimize this thing? So basically the definition is the following: partition the graph into k graphs on the same vertex set, add up the crossing numbers of your k graphs and try to minimize this sum. And k equal 2, as I mentioned, is relevant for electrical engineering. And the well-known concept, the thickness of the graph, is the minimum k, such that you can decompose your graph as a union of k-planar graphs. So that means that CRKG is equal 0. This is the minimum k, is the thickness of the graph. The question whether a graph is planar can be solved in polynomial time, whether a graph is biplanar, whether it can be partitioned into two planar graphs, it's NP complete. So, my interest is this alpha k constant. So what is this alpha k? I would like to figure out that how much I can gain relative to the crossing number if I allow a k-plane drawing. If I can make the drawing in k-planes, surely I don't need more crossings. So consider d numbers such that the k-planar crossing number is at most d times the crossing number. And what is the infimum of these d's which work for all graphs? This is this alpha k constant. So this is one of the key quantities in which I'm interested. So for biplanar crossing numbers, Owens in 1971 found this formula that the biplanar crossing number of Kn is at most 7/1536 times n to the 4 plus a cubic error term. And some people 50 years later improved on it, but only in the error term. So very likely that this is the biplanar crossing number of the complete graph. And some kind of numerology is that this 7/1536 is 7/24 times 1/64. So what is this 1/64? That's the coefficient in the n to the 4 term of the asymptotic formula, which is conjectured for complete graphs. So it is well possible that alpha 2 is 7/24, but we just don't know. Certainly alpha 2 is at most 1. So with Eva, Sikora, and Virtue 20 years ago, we proved that alpha 2 is at most 3/8. And that was a randomized algorithm. So start with an optimal drawing D of the graph G. The optimal drawing is one which exhibits the crossing number of graph. And then we do the following. Consider this as an application of graph labeling, since many people here are interested in graph labeling. So the graph labeling would go in the following way. You have the vertices of the graph and assign a label 0 or 1 randomly and independently to every node. And then assign labels to the edges as the mod2 sum of the vertex labels. So if two vertices got zeros, I denote those with the set of U. The edges between them, which would go somewhere here, gets a 0 label. W contains those vertices which got label 1. 1 plus 1 is 0 modulo 2. Edges here would get a label 0. And there are edges between these two kind of vertices. They get a label which is sum of 0 and 1, which is 1. And basically, the label of an edge would dictate whether I put this edge into plane 1 or plane 2. So, in the first plane, I put the subdrawing spanned by U, those spanned by W, which means both endpoints are in U or both endpoints are in W. They got the same label. And in the second plane, though the edges, as they were drawn in the original optimal drawing, between the two vertices which belong to two different groups, U and W. In the second plane, we have the UW type crossings. In expectation, this is 1/4 of the crossing number. And we actually have in the first plane many other type of edges. The crossings of UU and UU type edges. The crossings of WW and WW type edges, and UU, UW type of crossings. So far, we did not save anything. So with this kind of randomized drawing, you can reduce the number of crossings to the half. That's the obvious thing. Since whenever you put down the first edge, the second which crosses it either goes to the same plane or to a different plane. That's a factor of 2. So where is the saving? The saving is that these UU and WW type crossings can be eliminated. So you have U type vertices, translate them sufficiently far so that the connecting edges of them no longer crosses any edge of WW type in the original drawing. And in this way, we get the 3/8 theorem. So we also have a spanning tree problem connected to biplanar crossing numbers. So a conjecture. Conjecture is that we have a connected plane graph. So it's actually drawn in the plane. the drawing contains a union of edge-colored passes, and every pass has the same color. So you have a red pass, a blue pass, and a green pass, and other colored passes. And two such passes may intersect in at most one vertex. And then the conjecture is that if you have such a graph, then it's dual graph. The dual graph is drawn in the dotted lines here. It contains many loops, actually. Has a spanning tree with a root such that the rooted spanning tree, the dual graph actually can be colored using the colors of the original passes. So the dual actually crosses, every dual edge crosses exactly one edge of the graph, and I give it the same color. So if the dual edge crosses the red edge, it gets a red color, and so on. So the dual graph is colored. So the conjecture is that there is a spanning tree of this colored dual graph such that from the root is your choice, you can go to the leaves such that any root to leaf pass uses every edge color at most 4 times. Well, I would be happy with any constant here instead of, I'm sorry, I made a mistake. Wrong button. Thank you. So Jan Kinchel claims that he proved this conjecture, but he has not written it up in 4 or 5 years. So I don't know if he really has this proof or not. He is smart, and I believe that he is correct, but without a written proof, we are nowhere. So if Kinchel is correct, we actually can show that we can approximate the 7/24 for sufficiently dense graphs. So if n is sufficiently big and the number of edges is at least 1 minus delta time n choose 2, well, I mean for every epsilon I can select such a delta, that the biplanar crossing number of any G graph with this number of edges is at most 7/24 times plus this tiny epsilon times hn over the crossing number of kn. Well, that's supposed to be 1 if the conjecture is true, times the crossing number of G. So that's kind of a half of a theorem, since a basic thing is not written, as it depends on Kinchel's theorem. So we return to this problem with János Pach, Csaba Tóth, and Géza Tóth, and we prove that this alpha k gain factor for k-planar growings is between 1/k squared and 2k minus 1/k cubed. For k equal 2, we exactly get back the 3/8 theorem. This is exactly 3/8 for k equal 2. The lower bound here depends on the existence of the mid-range crossing constant. It does not depend on the value, just the existence. That's an interesting fact. And we pose the question whether k squared times alpha squared has a limit. So this k squared times alpha k from this formula is basically between 1 and 2. So it's a refined question whether this has a limit. So how the proof of this theorem goes? Pretty much the same way as the 3/8 theorem. So the idea is that we would like to map the edges of our graph into the complete graph K sub K with loops in every vertex. And this was the picture for K equal 2. This is for K equal 4. This is for K equal 5. So the idea is that we label the vertices randomly with residue classes modulo K. Those are the colors. And then for the edges, I just add up these two residues. And if the sum is P, it means that take the optimal drawing and move this edge to the P plane for P equal 1 to K. And where is the gain? The gain is that edges of the same color, like red here, red here, red there, are kind of big bunches of the graph. And these big bunches can be moved from a distance to each other, so that red edges here and red edges there, after a shift, no longer have intersections with each other. And you can make this kind of cleanup on every page, on every plane. And that's the idea. And later we had a project with Eva with a number of young people in a mathematical research communities workshop. And we actually answered positively the problem. Alpha K is determined as 1/K squared times 1 plus little o1 as K goes to infinity. We absolutely have no improvement on K equal 2. It's annoying, but we know what happens when we go to infinity. And we had an even more shocking result. If we ask the same kind of question, not for all graphs, but just for bipartite graphs, then we can answer the question exactly for every K. It's going to be 1/K squared. And the construction, oops, something happened here. No problem. So this is the Kirkman schoolgirl problem. So that was actually a problem in the Sunday supplement of a journal in 1847. So public then thought about this kind of problems. The problem was that we have 15 schoolgirls. Their names are from A to O. So these letters are the schoolgirls. And the schoolgirls, 15 of them, are supposed to walk in groups of 3 for every day of a week. Can they do it in a way that never 2 girls in 2 different days walk in the same group? And for 8 days, so the pigeonhole principle dictates it cannot be done. But for 7, it's iffy. You don't get a result that it is impossible, but you actually have to make a construction. And such a construction exists. And that's actually an instance of a resolvable, balanced, incomplete block design. So such an object with parameters S, L, and Y is a collection of M partitions, P1, P2, Pm, of an underlying S element set into L element subsets, such that every pair of points from the S element set is contained by exactly one of the MS over L element sets occurring as partition classes. And that one here corresponds to this exactly one. I did not introduce a parameter here since I did not need it. So the Kirkman schoolgirl problem is an instance of this for S equal 15, L equals 3. And for L equal 2, it's factorization of complete graphs into perfect matchings. So in a surprising way, this kind of block design thing is even better than the random labeling that I did, but still some randomization is needed to use this. So designs do exist, well, for sufficiently large base sets. And I'm running out of time. So for the bipartite case, to prove this 1 over k squared lower bound, we would have needed that for bipartite graphs, the crossing constant is the same. And we could not get the same constant for bipartite graphs. But we actually proved an version of the crossing constant theorem. So assume that C is a graph class which has at least one graph which has at least one edge. That's not a very strong condition. And in addition, the class should be closed for taking subgraphs, putting together two disjoint graphs from this class, and cloning a vertex. Cloning a vertex means that you make a copy of a vertex and join it to all neighbors of the previous vertex. If you have such a graph class C, then this kind of thing is convergent on this whole range for the number of edges of this graph. And actually, such graphs make many groups like KM3 graphs, C-colorable graph, in particular bipartite graphs and graphs with odd girth G. So actually there are infinitely many of such classes and they make a complete lattice. So I think it's about time that I finish it. I did not have time to reach several biplanar type questions, but I think that's it for today.
Thank you, Professor Laszlo. Now I would like to request Professor Bagga to felicitate him with a memento.
Well, let's have some time for questions. Are there any questions for the speaker? Any comments? Yes, there is a question back there.
So this is all for planar graphs, right? Like, is it extendable to higher dimensions or something? I don't know. I'm just asking some questions.
Well, actually, the crossing constant is the same if you make the drawing on any fixed genus.
Okay. Thanks.
Other questions? I see one more. Yes.
Sir, crossing number of complete bipartite and complete graph. Many studies has been done on these two type of graphs. Is there any other class of the graphs where we can study crossing numbers?
Well, there has been a lot of study for crossing numbers of concrete graphs and graph families, but crossing number in general is NP complete, and no class of graphs are known for which this NP complete problem would turn into polynomial time. So we don't know any class which is easy to compute for crossing numbers. But there are lots of results on crossing numbers published, since this is an old problem. There are many survey papers, and there is an annotated survey which goes on from somebody in the electronic journal. Markus Schäfer
Okay, sir. Thank you.
Sir, cloning vertex is similar to splitting graph.
Could you repeat it, please?
Cloning a vertex is same as splitting graph.
Same as splitting graph. Yeah, somebody called it splitting graph. Yeah.
Okay, thank you, sir.
All right, well, thank you very much for your interesting questions. Let's thank that. I'm pleased to honor exactly with this. Thank you very much.
Thank you.
Can you put up the next presentation so I can see the title? All right, we'll move right along to the next presentation of this session.
Nem tudtam elmondani.
Professor Gaur here is here. Yes. Thank you. Okay, so we are pleased to have as our next presenter for this presentation, Professor Atul Gaur. Professor Gaur is currently Associate Professor at Department of Mathematics at University of Delhi. He received his PhD from IIT Kanpur in algebra, commutative algebra, and he served in many other institutions in the last few years before moving to University of Delhi. His areas of interest and specializations are commutative algebra, multiplication modules, and algebraic graphs. So I'm pleased to welcome Professor Gaur. He's going to talk to us about, where's the title of his talk? All right. Professor Gaur, please welcome him.
Good afternoon to all. Thank you, Professor Bagga, for kind words. This one, huh? Oh, this and this one. Oh, all right, all right. So throughout my talk, all the rings are assumed to be commutative ring with unity. Here is the outline of my talk. Sorry. Can you help, please? Is it this one? This one? Okay, okay, all right, this one, okay, okay, all right, okay. Here is the outline. First, I'll discuss zero divisor graph associated with rings, then co-maximal graphs associated with rings, then maximal graphs associated with rings. And actually, we will see in zero divisor graph and maximal graphs, the set of all zero divisors play a crucial role for analyzing graph theoretical properties. So that's why it is quite natural to find all the rings with n zero divisors for any n. So fortunately, there is an algorithm that we will discuss in the end for any n, finding all finite reduced ring with n0 divisors. So the idea of associating a graph with the commutative ring with unity was first presented by Beck in the following paper. And the objective was to analyze graph theoretical properties with the rings, with the algebraic properties of rings, and the vice versa as well. So to associate a graph, Beck considered R as a simple graph whose vertices are elements of the ring R, and any two elements of R are adjacent if and only if the multiplication of X and Y is 0. So if you see from the definition, the non-zero divisors are just adjacent to the 0 element, right? So they all have the degree 1 vertex, so they do not play any, crucial role, important role while analyzing the graph theoretical properties. So a restriction of this graph on the set of all zero divisors was considered by Anderson and Livingstone in 1999. So actually Anderson and Livingstone named this graph as zero divisor graph, with the vertex set as the set of all non-zero divisors, and the adjacency condition remains same. So Beck actually focused mainly on the coloring of a graph, coloring of a commutative zero divisor graph. So here is the definition of chromatic number. Chromatic number is defined as the minimal number of colors required to color a graph such that no two adjacent vertices have the same color. Then we have the definition of clique. A subgraph C of a G is said to be a clique if every pair of distinct vertices are adjacent. If a graph G contains a clique with n elements and every clique of G has at most n, then the clique number of G is said to be n, and it is denoted by clique of G. So Beck focused mainly on coloring of a graph, and it is quite natural from the definition for any ring, or in fact for any graph, chi of R is greater than equal clique of R. Beck conjectured that chi of R equals clique of R for any ring. Actually, he proved this equality for several classes of rings. Like for R non-zero reduced ring, if chi R is finite, then he proved that chi of R equals clique of R. Similarly, if R is a principal ideal ring and chi of R is finite, then chi of I is clique of I for every ideal I, and hence, in particular, chi of R equals clique of R in this case as well. So since he couldn't find any example of a ring where chi of R is strictly greater than clique of G, so he made the conjecture. The conjecture was disproved in 1993 by Anderson and Nasir in the following paper. So to give a counterexample, they considered the ring, polynomial ring in XYZ over Z4, modulo the ideal generated by these many elements. So it's a ring where all the non-unit elements forms an ideal. So that's why it's a local ring. So these are the non-units of this ring. So it's a maximal ideal. It's the only maximal ideal. So it's a local ring. And for the clique, they proved that this set is a maximal clique. So clique of R is 5. And for chi of R, they considered the following subgraph. And it requires at least 6 colors to color this graph, as we can see in the next figure. So remember, because as per the definition, 0 and 2 will be adjacent to every other vertex, right? So in the figure, we have omitted the 2 vertices, 0 and 2. And for the rest, here is the picture. So to color this, we need at least 4 colors and 2 colors for 0 and 2. So that is why we need 6 colors to color this. So that means chi of r is greater than equal 6. In fact, it is exactly 6, as we have the following partition. Each partition will require a single color to color this graph. So chi of r is exactly 6. Another graph associated with commutative ring was considered by Sharma and Bhattacharya in 1995 in the following paper. So to associate a graph with a commutative ring with unity, they considered R as a simple graph with vertices, all the elements of R, and the adjacency condition is any two elements of a ring X and Y are adjacent if and only if Rx plus Ry equals R. That means the ideal generated by X and Y is the whole ring R. So if you see the adjacency condition, unit element will naturally be adjacent to every other vertex. So with this graph, they proved the following result. A ring is finite if and only if chi of R is finite, and in this case, chi of R equals clique of R equals T plus L, where T is the number of maximal ideals, because ring is finite, so semi-local, so it will have finitely many maximal ideals. So T denotes the number of maximal ideals and denotes the number of units. This result we generalized from finite to semi-local, we will see later. So this maximal graph was introduced by us, by myself and my PhD student Aarti Sharma in 2013. So to associate a graph, what we considered R as a simple graph with the vertex set, the set of all elements of R, and the adjacency condition is if there is a maximal ideal containing both X and Y, then both are adjacent. So if you compare this, if you see this adjacency condition, unit element in a maximal graph are just isolated vertices, right? Because unit cannot be contained in any maximal ideal. So in fact, if you consider this adjacency condition with the co-maximal graph, it is just diagonally opposite. So any two vertices in the co-maximal graph are adjacent. That means ideal generated by X and Y is the whole ring R. If ideal generated by X and Y is the whole ring R, naturally the X and Y cannot be contained in the any maximal ideal. So X and Y cannot be adjacent in the maximal graph. Vice versa as well. If X and Y are adjacent in a maximal graph, that means there is a maximal ideal containing both. So they cannot be adjacent in co-maximal graph. So basically this maximal graph is just graph theoretical complement of co-maximal graph. So, and because as I told you, the unit element do not contribute anything while analyzing graph theoretical properties for a maximal graph. So it is quite natural to consider this maximal graph with the vertex set restricted to the set of all zero divisors, set of all non-units. So this graph we considered in the following paper in 2017, where we generalized the Bhattacharya's result, this one from finite to semi-local rings. So from the definition of maximal graph, it is quite natural that every maximal ideal forms a maximally complete subgraph, but the converse need not be true. For the converse, you take a ring as a Cartesian product of three fields, K1, K2, K3. Then you consider this subset of R. It's a maximally complete subgraph, but it is not even an ideal. Forget about the maximal. So on a maximal graph, we proved the following, that clique of R is finite if and only if R is a finite ring or is a field. So next we tried whether the clique of R equals chi of R, and for semi-local ring we proved this So we proved the equality by using the following lemma. So first we proved this. So if R is a semi-local ring and M1, M2, Mn be the maximal ideals such that the cardinality of M1 greater than equal cardinality of M2 and so on, then in any minimal coloring of a maximal graph associated with R, Mn have the colors already used in the colors union Mi from 1 to n minus 1. And using this, we proved that for a semi-local ring, chi of R equals clique of R equals the cardinality of M, where M is the maximal ideal of R of the largest cardinality. So then we talk about the graph isomorphism. Recall the two graphs A and B are isomorphic if there is a bijection between their vertex set which that preserves adjacency condition. So it is quite natural to ask if the maximal graph of two rings are isomorphic, does the rings are so? So it is not the case. For example, you consider the following two rings. One is Z9, other one is Z3x modular, the ideal generated by x square. Both are local rings, have a maximal ideal of cardinality 3. So if you go with the maximal graph, you will get one triangle and then 6 other isolated vertices. So the maximal graph of A and B are isomorphic, and it's quite natural the rings are not isomorphic. So then we tried to find some condition under which we get the isomorphism between the rings from graph isomorphism. So first we observed the following proposition. If R and S are semi-local rings, so here GR, GS denotes the maximal graph associated with R and S. So if the GR and GS are isomorphic, then for every maximal ideal M of R, the image of M means phi M is a maximal ideal in S. So that means both R and S have the same number of maximal ideals. And then we tried to answer partially on the isomorphism between rings. So if you have these RISI family of finite local rings, R the Cartesian product of R1, R2, Rm, S the Cartesian product of S1, S2, Sn. So if the maximal graph of R and S are isomorphic, then M equals N, and there is a permutation sigma such that the cardinality of R mod Mi is equals to the cardinality of S sigma I mod N sigma I, because R mod Mi is the unique maximal ideal of Ri. So R mod Mi is a field. So basically they are fields of the same cardinality, and for any prime power there is exactly one field, so up to isomorphism. So basically they are isomorphic. So in particular, when both Ri and in particular if Ri is a field for all I 1 to M and the maximal graph of R and S are isomorphic, then we get the isomorphism between rings R and S. So here is the basic definition of complement of graph. The complement G dash of a graph G is a graph with the same vertex set and with the property that any two vertices in G dash are adjacent if and only if they are not adjacent in G. So in general, the following need not be true. Clique of G equals chi of G if and only if clique of G dash equals chi of G dash. For example, you can consider the following graph. This is graph G. This is its complement. So if you look at G, the clique of G is 2, chi of G is 3. But in G dash, both clique of G dash and chi of G dash both are 3. However, for a maximal graph, both the equalities hold independently. So for a maximal graph of a finite ring, so for a maximal graph of a finite ring, clique of GR equals chi of GR, and this we proved. And then for the complement, because GR dash is just co-maximal graph, so this was proved by Sharma and Bhatt-Badekar. So here is the generalization from finite ring to semi-local ring of Bhatt-Wadeker's result. For a semi-local ring, we proved that clique of gr dash equals chi of gr dash equals n plus the cardinality of unit elements in R. So n, where n is the number of maximal ideals in a ring R. So next we talk about the Eulerian graph. So first we prove the following algebraic property for a finite ring. If R is a finite ring, that is not a field, then the cardinality of R is odd if and only if every maximal ideal is of odd cardinality. So recall a closed walk running through every edge of G exactly once is called an Euler line, and a graph that contains an Euler line is called an Euler graph. So what we proved, this gamma R denotes the maximal graph where the vertex set restricted to the set of all non-unit elements of R. So R is a finite ring that is not a field, and gamma R is the maximal graph vertex set restricted to the set of all non-units. Then gamma R is an Euler graph if and only if R has odd cardinality. So if you club this with the previous result, because in the previous result we proved that R has odd cardinality if and only if every maximal ideal of R has odd cardinality. So gamma R is an Euler graph if and only if every maximal ideal of R has odd cardinality. So now we talk about the algorithm of producing all finite rings with n0 divisor, all finite reduced ring with n0 divisor for any given n. So if you recall from the structure theorem, any finite ring R can be uniquely determined as a finite direct product of finite local rings. So it is quite natural to think about the cardinality of finite local ring. So here is the theorem related to the cardinality of finite local ring. If R is a finite local ring with M its unique maximal ideal, then the cardinality of R is P power nm, where P power n is the cardinality of the field R mod M, and M is the length of R as an R module. So in fact, to see this, you can consider a composition series for R. Composition series means length of ascending chain of submodules, so that every quotient is simple. So because all these quotients are simple, so any simple module is isomorphic to R mod M. Any simple R module is isomorphic to R mod M for some maximal ideal M, because the ring is local. M is the only maximal ideal, so all such quotient will be isomorphic to R mod M. So, and the cardinality of R mod M is P power n. So the cardinality of all such quotient will be P power n. So cardinality of R, which is the direct product, actually all the terms in between will cancel out each other. Only the Im and then the cardinality of 0 will left. So that means all these quotients are of the cardinality P power n. So it is eventually P power n m. So for any finite ring, because structure theorem says any finite ring, you can write it as a product of finite local ring. For the finite local ring, that they are of the cardinality of the form pi alpha I for some prime pi and natural number alpha I. So cardinality of any finite ring will be of this form. So in fact, for any finite, if the ring is reduced ring means the nil radical is 0. Nil radical means the set of all nilpotent elements is 0, right? So 0 is the only nilpotent element. So any finite reduced ring is uniquely determined as a finite direct product of fields. So that comes directly from the structure theorem. So, and for any field, we know for any prime P and for any natural number n, there is a unique field of P power n cardinality. And if you have a field, finite field, then it will have cardinality of the form P power n for some prime P and n. In fact, this prime P is the characteristic of the field. So any finite reduced ring is uniquely determined as a finite direct product of fields. So now first we talk about the finite ring with p power k zero divisors for prime, any prime p and any natural number k. So one thing to observe, if you have a finite ring, element is either zero divisor or non-zero divisor. If it is a non-zero divisor, let's say A is a non-zero divisor, then you consider the map from R to AR. Basically, X goes to AX. So because A is a non-zero divisor, it's a 1-1 map. You have a 1-1 map on a finite set, it must be onto. It must be onto, that means AR equals R. AR equals R, so A is unit. So that means every non-zero divisor in a finite ring is unit. So that means in a finite ring, either an element is a zero divisor or it must be unit, right? So, and finite ring, finite reduced ring, we can write it as a product of the Cartesian product of fields. So you consider the ring FPK. FPK is the field with p power k elements. So consider the polynomial ring in X over FPK modulo the ideal generated by X square. It's a local ring with with p power k non-units. That means because every non-unit is a zero divisor, so p with it's a local ring with p power k zero divisor. That's what we listed all the elements of this ring, and this together with zero is the maximal ideal. So that means these are the only zero divisors in the ring. So p power k zero divisors. So this theorem is due to Redmond, and because of this theorem, we will be able to determine all the finite reduced ring with n0 divisor for any n of your choice. So R is a finite reduced ring. If k is the smallest positive integer such that cardinality of R is strictly less than 2 to the power k, then R is a product of k minus 1 or fewer fields. And it's quite natural because the smallest field is of cardinality 2, Z2, right? So even if I assume R is a product of Z2, let's say suppose it is a product of k copies of Z2, then the cardinality will be 2 to the power k, which violates this. So R is a product of k minus 1 or fewer fields. And if you suppose you have a k copies of Z2, right? So what are the zero divisors or what are the non-zero divisor? Non-zero divisor means unit. So in Z2 cross Z2 cross Z2 k copies, only 1, 1, 1 k tuple at every place, the 1, it is the only non-unit. So in in Z2k, the number of zero divisors is 2 to the power k minus 1. So the second result in this direction, if R has n zero divisors and k is the smallest positive integer such that n is strictly less than 2 to the power k minus 1, then R is a product of k minus 1 or fewer fields. And because if R is a product of, let's say, k fields and each of them is Z2, then the Z2 Cartesian product of k copies of Z2 will have the zero divisor 2 to the power k minus 1, which will violate this. So that is why R is a product of k minus 1 or fewer fields. So this is the justification as I already covered. Now, any finite reduced ring is of this form for some finitely many fields, right? So now, what is the zero divisor in this ring? Basically, in a finite ring, either an element is a zero divisor or it must be unit, right? So what are the unit elements in this ring? Unit element will be when every tuple is unit in their respective field, right? So that means what are the non-unit element? Non-unit element is any such tuple where at least at one place it is 0, right? Any k tuple where at least at one place this xi is 0. So the number of non-zero divisors in this will be given by this. This I am calling the number of non-zero divisors in this ring. So it is this term when we take exactly one coordinate 0 at each place, this term when we take exactly two coordinates 0, this term when we take exactly k minus 1 coordinates 0, right? So because of this, now I can talk about the algorithm. The algorithm was given by Redmond. So now suppose I want to determine all finite reduced rings with n0 divisors. So what we do? Determine the least k for which n is strictly less than 2 to the power k minus 1. With such n, what we do? We find the solution of this where xi's are of the form. Remember, if you go back, the cardinality of these are, because these are the cardinality of fi's are field. So fi star, the means fi minus 1. So the every field is of cardinality pi power alpha I. So cardinality of fi star is pi power alpha I minus 1. So xi's are of the form pi alpha I minus 1 for all I, for some prime pi's. So find the solution of this for all j from 2 to k minus 1. For each such solution, if let's say p1 alpha 1 minus 1 here, p2 alpha 2 minus 2, pj alpha j minus 1 here, if we is a solution of this equation, then fp1 alpha 1 cross fp2 alpha 2 cross fpj alpha j is the required ring with n0 divisors. So each solution will give me a finite reduced ring with n0 divisors. So let's see an example. Suppose n is 10. So the least such k will be, satisfying this will be 4. Then for 4, k equals 4. First you find the solution of this. Remember, xi I can take pi alpha I minus 1, right? So determine the solution of this. These are the only possible values. Each of these number is of the form pi alpha I minus 1 for some appropriate prime and some appropriate natural number alpha I, right? So if this is the for this solution, I am getting f2 mod f2 cross f9, the ring with 10-0 divisors. For this solution, I am getting f3 mod f8, the ring with 10-0 divisors. Similarly, for this, I am getting f4 mod f4 cross f7. And then for consider this. So for this, I am getting, this is the only solution, right? So f2 cross f3 is the required ring. So these are the only finite reduced ring, these 4 with 10-0 divisors. Similarly, this is another example. In this case, we computed the all finite reduced ring with 15-0 divisors by the same algorithm. And these are the references. Yes.
Are there any questions? Yeah. Yeah, go ahead.
Hello, Dr. Gors. You started your talk with the rings and the associated graphs for which the chromatic number is equal to the click number.
No, I mean basically the for the 0 divisor graph, chi of r equals to click of r was conjectured. The conjecture was disproved then. But for maximal graph of all the finite ring, chi of r always equals to click of r. Even for semi-local ring as well. That's what we have observed.
So that means the graphs which you considered as the direct product of, so this equation is satisfied.
Chi of r equals click of r for every maximal graph of a finite ring. For a semi-local ring even.
For maximal
for a maximal graph, not for 0 divisor.
Thank you.
Yeah, please go ahead in the back.
Sir, what is the role of unity in defined zero divisor graph?
What is the role of?
Sir, you have taken commutative ring with unity.
Huh.
What is the role of unity in defining zero divisor graph?
Well, zero divisor graph, people are talking about the zero divisor graph for ring without unity, even for the non-commutative rings as well. So, I mean, people are working in that direction as well. But of course, I mean, because, you know, I mean, the commutative ring and non-commutative ring, the theory will go exactly opposite. I mean, it is, I mean, if you go with the definition, it's simply the multiplication is commutative or not. But then when you go inside, the theory is completely opposite.
Sir, my question is, what is the role of unity? If we define zero divisor graph, why is unity used? And what about the zero divisor graph in arbitrary rings? Yeah, can we define zero divisor graph on vector spaces or any other continuous
No, we
functions?
cannot talk about the zero divisors for a vector space. Zero divisors are only for rings. Zero divisors are in the rings, defined for rings, right? So of course, whether it's commutative or non-commutative, you can talk about the zero divisor.
Sir, you have written this chromatic number is greater or equal to clique number.
Huh.
Sir, I want the ring graph of that ring and explain construction of that ring. Sir, you have given the country this chromatic number greater than, where it exists specifically greater than.
Got it. Huh.
I want a construction of that ring and that graph very well.
You want the construction of that ring?
Yes.
It's a polynomial ring in XYZ over Z4. It's a ring with 32 elements, right? So the R mod M, the maximal ideal, which I told you, that has 16 elements. So R mod, if you consider R mod M, that is isomorphic to fields. So basically, I mean, for the zero divisor graph, I mean, if it is a unit element, do not play any role, right? So the crucial role will be the elements within the M.
Okay, thank you, sir.
Thank you. Any other questions? Yes, please.
Good morning, sir. Sir, suppose there are three fields, F1, F2, F3.
F1, F2, F3, all right.
Field F1 with P1 elements, field F2 with P2 elements, field F3 with P3 elements.
All right.
So can we count the number of non-zero geodesics like this? Means total elements of F1 cross F2 cross F3 will be P1 into P2 into P3.
In F1 cross F2 cross F3. So
total elements are P1, P2, P3.
All right.
Okay.
So
now in this, the units will be P1 minus 1 into P2 minus 1 into P3 minus 1. Because the first, right?
Right.
And if you remove 0, 0, 0.
Rest
so
all are units.
Yeah.
Rest
so
all are non-units.
Non-units, yes. So among that, if you remove 0, 0, then the remaining will be non-zero devices.
Right.
Yeah. Okay. Right. Thank you, sir.
Any other questions? Oh, thank you. So let's thank Professor Gar once more for a nice talk. Thank you. Thank you. Please do. Please stay to God. Thank you.
I'm really pleased to meet you too.
Thank you.
Hello, Deepakshi. Nice to see you after a long time.
So please be seated for a minute. I would like to thank Professor Laszlo and Professor Atul Gaur for their inspiring invited talks. A special thanks to Professor J. Bagga for chairing the session. Now we will be proceeding for lunch, and exactly at 1:45 we'll be starting the next lecture. So it is really requested that we start on time. And the other two announcements are that if you want to collect the fee receipt or any other receipt, then it will be mailed to you online. You do not need to come to the desk. But if you want to have the duty slip, which is your relieving slip, then you can collect it from the given place outside, decks outside. You can collect it from there. but you have to give it now because it'll be taking some time for approval from our side. So if you want in the evening, you have to go and do the process right now. So we'll go for lunch now. Thank you. Thank you. Good afternoon, everyone. Welcome to the last and final session of this final day of International Conference on Graphs, Networks, and Combinatorics. So this session will be chaired by Professor Andrea. Professor Andrea is an associate professor currently serving in Department of Applied Mathematics and Information in Faculty of Mechanical Engineering, Technical University of Slovakia. She has published a lot of papers and research, but the area is mathematical graph labeling and predetermined weights. So without any further ado, I call ma'am to please chair the session.
Good afternoon to everybody. Sorry that we are late. I would like to introduce our first speaker of our afternoon session. Today, first speaker is Dr. Takeshwar Singh. He has completed his PhD from the University of Delhi, and his thesis title was Advances in the Theory of Signed Graph. Presently, he is appointed as a professor at BITS Pilani, Goa. He has 26 years of teaching experience and 22 years of PhD research experience. He supervised many several doctor students, and he is very active in some editorial board of some journals. And I would like to invite him to present his talk, please.
Thank you, Professor Andrea, for a small introduction. First of all, I thanks to Dr. Ajay Singh, who has given me opportunities to share my research work, some of the recent research work. My title of the talk is on local distance anti-magic coloring of graphs. And Professor Hegde, Professor Andrea has discussed about the labeling problems. And especially she has done about the local anti-magic and other variation of the coloring. So today I'm just going to give the local version again, what is the problem and what are the things we are doing and what are the things we have to do in future. So basically that distance magic labeling started from that. One paper was here. Magic square, everybody knows about the magic square. So if you are going to consider any magic square here, so suppose we have a magic square 3 cross 3. So we know that there are 9 numbers we have to fit into the squares in such a way that the row sum, this is a row sum, this must be a constant k. Column sum must be also the same constant we have to get. And diagonal elements, if I'm going to consider that, so this diagonal elements must be also same. And this diagonal elements must be also the same. So it's very easy to find out what is the value of k. We have 1 to n numbers and n cross n is magic square is there. So you can easily find out what is k here. So there are 2 versions here. We can label the vertices of the graph or edges of the graph in such a way that we are going to define our vertex and edges both we can label. So this is the outline of the talk. First, I'll just give you some times for introduction to distance magic graphs, distance anti-magic graph, then locally anti-magic graphs, and some references. So throughout the lectures, what I'm going to consider is a simple graph with the vertex at V and a set E, and we assume that number of vertices in the graph as a N and number of edges in the graph as a M. Okay, so labeling is nothing, as you know that one, it is nothing but the assignment of numbers. So the vertex elements of the graph, vertices, edges are both. Okay, now then we are going to say something, some conditions we are going to put on that one, and if it is satisfying certain conditions, then we are going to get that. Okay, so in this case, what we are going to do that one. So if I'm just going to take the label here, so there is a one version when we are going to consider the vertex version. So I am going to consider a partition. This is a one partition. This is another partition on the number 1 to n. Okay, so it is easy. You can say that one. This is 2726 here. Sorry, 276, 951, and anything 438. This is a magic square of 3 cross 3. Okay, so if I'm just going to consider here the numbers which is given in this row, so that is 2, 7, 6. Consider the vertex set whose label is 276, and then second set 9, 5, 1, and third set sorry. So what I'm going to do here, that is a problem here. Here 2, 7, 6. Then here we have 9, 5, 1, and then we have here 4. Am I right? 4, 3, 8. So these are the partitions of the numbers from 1 to n in 3 subsets. You can say that one. So this is a partition of the number in 3 subsets. If I'm going to consider a complete 3-partite graph here, okay. So if you are just going to take this as the vertex of the graph whose label is 2, this will be adjacent to all the vertices in this set, all the vertices in this set. Okay, and if you just take the neighborhood of this one, so these are the vertices whose label are 9, 5, 1, 4, 3, 8. These are the neighborhood of that one. If you take the sum, so what we are going to get? This is 15, this is 15, this sum is 30. Okay, this sum is 30. Now for this, if I'm going to consider this vertex here, we know that this is adjacent to all the vertices here and all the vertices here. Again, we are going to get here 30. So again, this is a constant number we are going to get for all such vertices. So this is called a vertex leveling, which is introduced, which came from the magic square and introduced as a distance magic leveling of the graph. Then another version is, if you just consider the same magic square, so I'm just going to keep it here. I'll not do the same mistake. 276, 951, and 438. Another way, if I'm going to label, take the complete bipartite graph, K33. There are 9 numbers are there. I'm going to consider the K33 here. So this is a vertices in the one partite set. And this is a vertices in the another partite set. I'm going to consider here. And this vertex, you know that it is a complete bipartite graph, so it will be adjacent to this one. So what I'll do, I just take the label of the first row, I assign to the edges here, say 2, then 7, then 6 here. Similarly, I take this vertex and join to other, and then I just label this one 9. So this edge is labeled as a 9, this is 5, and this is 1. Similarly, you can do that. So for this one, you are going to get here, label the vertex as a 4, the edges as a 4, 3, 8. Again, you can see here what we have done, we have labeled the edges of the graph from 1 to 9, because the number of edges are 9. And if you consider this vertex, take the sum of the edge labels. Okay, so sum of the edge labels. What we are going to get here, 2, 7, 6, that is 15. Here also you can check that it's 15. This is also 15. So we are going to get the constant sum. So this is called the edge version. So when you are going to label the edges in such a way, and calculating the weight of the vertex. Then if the weight of each vertex is going to be same, we can say this is a distance, edge distance magic. This is a vertex distance magic. Okay, so here distance is just taking the one distance neighborhood of the graph. Okay, so these are the two things, and later on, lot of literatures are there. There are so many versions were there in the literatures for that. Those who are wants to work in this area, please follow the Galilean survey on graph leveling problems. Okay, so here with vertex weight, edge weights, and other things we are going to discuss. And you take a number 1 to m plus n. If there are n vertices, m vertices, label the vertices as well as edges, and put some conditions to calculate the weight of the edge or weight of the vertex. Then it is known as total edge leveling. Professor Hegde and Andrea has already focused that one. So I'm not going to spend much time on that. So here is the simple one. This is another magic square with 4 cross 4, and these are the numbers you have distributed. And same thing, you can do that one. So this magic squares can also help to partition the set of numbers. Okay, so here we have to 1 to 16 numbers. We have to partition into 4 sets, such that if you take the sum of each numbers in the particular set, it will be always constant. And in general, this is a integer partitioning problem. In general, is very difficult. So formal definition of the distance magic graph is what is given here. So what we have done in this case, we have taken the magic squares, and then we have considered the partite sets, and we label the vertices as the entries in the magic square row wise, and then we calculated the weight of the vertex. So it means we have labeled the vertices, then we have calculated the weight. So that is why the definition is now. So if you have a graph of order n, and if you label the vertices from 1 to n and calculate the weight in this manner, so if you take all the vertex which are in the neighborhood of V and take the vertex label and sum it, if it is constant, then we can say that this labeling is a distance magic labeling, and the magic constant, this constant k is known as a magic distance magic constant. So it's very easy to find out the magic distance magic labeling of this one. Anyone? Participants? What should be the labeling here? 5 vertices are there. Okay. You can see this vertex is adjacent to all the vertices here. So this you can label as a 5, and remaining you can label as a 1, 2, 3, 4. And just see, it is always a magic constant. So this is a complete graph, but I have removed this edge, which form a maximum matching in this one. This is also distance magic labeled graph. Then Yashin and Simanjutek use the heuristic algorithms to find out the all possible distance magic graphs. Okay, so this is a simple one survey up to non-isomorphism, up to 9, you know that one. These are the graphs which are non-isomorphic, and these are the only graphs which are distance magic, and computation time you can see here. Okay, and these are the all possible graphs of order 9 which are distance magic. So these are the up to order 8 here I have listed here. Then Professor Armugam and his student Kamachi discuss about the distance anti-magic labeling. So in this case, what is happening is we are labeling the vertices, and then we are calculating the weight in the same manner. But we say that it is distance anti-magic if weights of each vertex, all the vertices are distinct. Okay, all the vertices are distinct. So this is a definition of the distance anti-magic graph. So in this case, you can see if there are 2 vertices in the same neighborhood, they cannot be distance anti-magic. Okay, if there is a graph in which 2 vertices have the same neighborhood, it cannot be a distance anti-magic graph. So these many results are there in the thesis written done by Kamachi under the guidance of Professor Armugam, and these are the some results I have quoted here. Okay, not many. There are many results are there and wonderful thesis, and in that thesis also they have, professor has proved, given a proof, very elegant proof that distance magic graph constant will be always unique. If there is a graph which is distance magic, then it is always unique. And simultaneously, then Professor Slater and his students have also proved the same uniqueness of this one. So in this thesis, as you know that Wn is nothing but the, if you take Cn and join a vertex in the central, that is a Cn plus K1, join K1. So he asked that one, if G is a distance centimetric graph, is it true that G plus K1 or G plus K2 are distance centimetric? Okay, to tackle these problems, what we have done, we have just defined, we asked a general question, we just try to tackle the general questions that if G and H are the distance centimetric graph, is it possible to have a distance centimetric labeling for G join H? So we have defined a new labeling, which is called as a arbitrarily distance anti-magic labeling. So first we have a labeling F. It is a distance anti-magic of the some graph G. Then we take a integer K. If this is going to be the new labeling Fk of the same graph as a 1 plus K, 2 plus K, and plus K, where the new labeling is defined as a old labeling of this plus K. And the vertex weights are different for every pair of vertices, then we say that it is arbitrarily, because K can be any integer greater than or equal to 0. Okay. So this is a way we just do that one. So if you take any regular graph, if it is distance centimetric, if you add any constant, it will be automatically a distance centimetric. Okay, so we say that one. So we proved many results on that one, and then we found some necessary and some sufficient conditions. And then we said that if that is going to be satisfied, then this G1 join G2 will be distance centimetric, and proved many results on that one. Okay, let us come to the, because I need a local anti-magic labeling to prove some results on the local anti-magic labeling of the graph. As you know, this is just repetition. We have a graph, and we define this is an edge version. We are labeling the edges from 1 to M. We say that it is a local anti-magic labeling. If you take any pair adjacent vertices, pair of adjacent vertices, the weights which is calculated as a sum of the vertex labels which are in the neighborhood of U and V. Okay, if it is distinct, so here we are just going to take that one, whatever the edges coming to this one, we are just going to take the sum of the edge labels here, which is WU. Similarly, WV we are going to calculate. If the pairwise distinct, this adjacent vertices getting a distinct weight, we say that it is a local anti-magic labeling. And this local anti-magic labeling, which induces the weight of the vertex, is going to be give you the proper vertex coloring of the graph. And it was initiated by, the work is initiated by Professor Armugam, and many results are there in the literature, and he posed on conjectures also. So in this case, so local anti-magic chromatic number is defined as a chi LA of G, which is nothing but the minimum number of colors used over all coloring of G in this manner. Okay, if I just take chi G as a usual chromatic number, so you can easily observe that chi LA will be always greater than or equal to chi G. For example, if you take a star, so here if you are going to take the star and label the vertices, label the edges as 1, 2, and 3, then you can see these vertices are going to label the weight, the weights are 1, 2, 3, and for this vertex it is 3 plus 2 plus 1, that is 6. So we have 4 weights. Okay, and it is a proper vertex coloring. So in this case, it is 4. Chromatic number is 4. Local anti-magic chromatic number is 4, but chromatic number of this graph is 2. So you can say K1n, you can consider it is arbitrarily like that. So this is very easy to observe that one. Then The concept of anti-magic labeling was also introduced by Hurstfield and Ringel, and he posed the conjecture that every simple connected graph other than K2 is anti-magic. Then, as I told you that Professor Armugam in 2017 conjectured that any connected graph other than K2 admits a local anti-magic labeling. Oh, sorry, I typed 2 times here. Typo. Okay, local anti-magic. It's very simple because it is a K2. You have a one edge. You have to label that one. And for the end vertices, same vertex weight we are going to get, which is not a local anti-magic labeling. So he posed the conjectures, and in 2018, using probabilistic method, Hasselgrave has proved that this conjecture is true. Okay. Now in this case, what I'm going to do here is I'm just going to take the help of a local anti-magic labeling, distance anti-magic labeling, and then magic rectangle sets. So let us define that one. So magic rectangle is very simple to the magic square only. So if you take a magic rectangle of 3 cross 5 or 3 cross 4, so you have to label arrange the numbers 1 to 12 in the 3 columns and 4 rows in such a way that the row sum will be one constant, column sum will be another constant. Like that, we have to do that one. So this is a way we are going to take the help. So here I'm going to consider that magic rectangle. So here, if I just take the numbers, so here we have 3 rows here and 4 columns, and it's easy to find out a necessary conditions that if n satisfied something and m satisfied the conditions, then you can have a magic rectangles here. So here, this row sum will be a constant. So suppose this is a capital K, and then column sum will be also constant. So let us say capital M. So these are the constant we are going to consider. If it is a square, then it is a same. M and K and M are the same here. So here, so we have a numbers 1 to ABC, and we are just going to take the array as a cross B only. So A rows and B columns, you can say. If I'm going to take the sum in each row, it will be like this, and column sum will be like this one. Okay. So these are the some conditions that when it will be exist and what is the conditions are there. So I use conditions this theorem for getting the bounds. Then here we have another result that if ABC are positive odd integers such that 1 is less than or equal to A is less than or equal to B, then magic rectangle set exists. Okay, so these are the some results I'll be using in the later part of this one. Then I was working on that path and other things, and I gave a lecture where Andrea was also one of the speakers, and she told that we have also proved the same results. Okay, so I got a paper from the Andrea, and it was published in Symmetry. Am I right? Yes, it is published in Symmetry in 2020, I think, 20 or 21. 21. Okay, so we are working in, but the proof that they have taken the approach is different from our proof. That is something equally two edge coloring schemes they have used and proved that one, and same bounds obtained. So we have also obtained the same bound, and these are the conditions we are knowing that one. So here, if n is even, then we have if you take any union of this R copies of Cn, it is locally anti-magic, and chromatic number is 3 here. Okay, chromatic number is 3. So I'll just use next. Okay, I'll just clean then this one full. So in this case, what is a simple one? If you take here C3, you are going to label the edges 1, 2, 3. You can see. So this is a graph. And if I'm just going to calculate the weight, and all the weights are distinct here. So in this case, we have 4, and here we have 3, and here we have 5. These are the weights we are going to get, and these are the colors of the vertices. So there are 3 colors we are going to get here. if we take C4, so in this C4, what we are having that we have to label the vertices 1, 2, 3, 4 in such a way that we can label it like this 1 and 4 here, 2 and 3 here. So this weight will be 5. This weight will be 5. So 2 weights are same. We can do that one. And this is now you can see this is 6 and this is 4. So we need here 3 colors. So that is the idea. And in general, it was proved here. I hope that I'm in the time, matching with the time. And then this was the up to this same results we have proved, and Professor Andrea and Martin Becha and Taumin Wang, they have also proved. Their approach was different, my approach was different. And after that, there was a question here. Okay, this was also done, that one. So this proved, to prove that one, that if you take a complete bipartite graph, union of that one, R copies, it will be 2, if and only if n and m congruent to 0 mod 2 are, this product is 1 mod 2. Okay, this product is 1 mod 2. So if you remember the previous one, the magic rectangle set, this condition, so we are getting from this one only. So using the help of this magic rectangle set, A is congruent to A and B are congruent to 0 mod 2, or ABC is 1 mod 2. This conditions I am using that one, and it is easy to prove that if I take A here, n is greater than or equal to 4, m is greater than or equal to 2, then this will be always 2. This will be always 2. Okay, so this is a way we are able to get that one. Now, the same magic rectangle set can be used to prove that if you have a G with P vertices and Q edges, because I have taken here M and taken the modulo, and R also I have taken. So consider this graph as a G, locally anti-magic, with the local anti-magic chromatic number is R. Then if you take the corona product, so what is the corona product here? So here we have a graph. So suppose this is my graph, and you can consider this is a graph, vertices are somewhere. So each vertex I am going to use, attach a graph. So here Km complement I have done that one. So here say let us say K3 complement. So these are 3 vertices I am going to attach to this one. So every vertex we are going to attach like this one. Okay. And I have considered the vertexes in this graph as a P. So there are P vertices here, P vertices. And here I'm going to take M, okay, because this is a Km complement. And you know that we have a magic rectangle set. When it is going to exist, that conditions we can use here. Okay, so this is a conditions when P is M mod 2, then we can find out that one. So what I'll do here, I'll just take the one column of the magic rectangle, okay, and label the vertices of this one part of the Km. Similarly, I'll just take another vertex here, which is attached to this 3, and then I'll take the column entries of the column of that magic rectangle set attached to this one. So basically, what we are going to do that one, we are labeling the edges like this, which are the entries of the column of the magic rectangles. So this sum is going to be contribute the same actually. This sum is constant, this sum is also constant. The weight of this vertex is not going to change that. Only thing is we are just going to take the different color to this one because this is a pendant vertex. So pendant vertices are going to get a different colors. So how many pendant vertices we are going to add it here? That is a Km complement. So P vertices are here. So P, M times P, and then extra colors, which is going to be this one only. Because original graph G, so in this case, original graph G is a locally anti-magic, and with local anti-magic chromatic number is R. So inside that, inside this one, the weight is not going to disturb, okay, because we are going to add only the constant, so it will be the same. This coloring will be the same. Only the coloring we are going to get on the pendant vertices. That's why this bound is attained here. Okay. So it's very easy to see here. So if we take a graph G and if we take KT complement, then it will be always greater than KT complement. I'm just taking the joint operation here. So this is the 1 plus the chi-LA of G. So if you know the graph whose local antimagic chromatic number is some R, we can construct a graph H from that graph with the local antimagic chromatic number of that graph plus 1. Okay, so you can give any numbers. We can construct a graph with the local antimagic chromatic number is equal to that number. That is another very simple approach here. Using the same conditions, we are going to do that one. So what we have here, let us take a small example. Okay, so what I'm going to do here, suppose this is my graph G, and here is a, let us say, we have a K3. We know that local antimagic chromatic number is 3 in this case. Okay, so what I'll do, I'll just take a magic rectangle set. Okay, 3 cross n, something like that. I can take that one. So I'll just consider the magic rectangle set satisfying the condition 3 cross n, where n is satisfying that conditions, that one. So here I'll take a vertex, I'll join to this one. So when I join to this one, I label these edges by the entries of the column of the magic rectangles. So if I'm just going to take the entries like say C1, 1, this is C1, 2, this is C1, 3. So this is the first column of the magic rectangle, entries of the first column of the magic rectangle set. Similarly, if I take a vertex here and just join like this, so I'm going to add here again C21, C22, like that, C23, and we'll get that. So in this case, you can see the weight of this vertex and weight of with this vertex will be always constant, because these are the entries of the column of the magic rectangle set, and it is always a constant. Okay, so the coloring of this weight is going to be the same. So whatever vertices we are going to add here, we are going to color that vertex by a single weight. So only one color is required, and since this sum is always, we are adding that one. This number is nothing but the entries on the row. The entries on the row is again a sum of, it is a constant. So this weight will be also added by, suppose earlier it was some R, then it will be added by some capital K, like that. So this will be intact. The coloring of the original graph will be intact. That's why we can construct many such graphs from the previous graph, whose chromatic number will be just 1 more than that one. Okay, so here we put the condition because that n should be even, or the condition of the magic rectangle set. So this is a simple corollary to that one. And here, this is a graph. We are going to get here 1 plus this one. Oh, sorry, this is not K3, this should be K3 actually. So in this case, we are going to find out if take any number, give me any number, I can construct a graph with the local antimagic chromatic number as that number. So that is a very simple approach we have taken here. Now, there are, okay, before going to that, there are many other things we have done that one. So let me erase some of the parts here. I think this is going to be help. No, this is not going to help me. This is a color, that is a, this is a eraser, I think. Now it is okay. Okay. Then we have started finding out some graphs whose chromatic number. Professor G.C. Lau has given a lot of classes of graphs constructed from cycles and paths whose chromatic number is same as a chromatic local antimagic chromatic number is same as a chromatic number of the graph. So in this case, he has proved many results such that this will be always equal to that. Okay, so he has proved that one using the path and cycles. So what we have done, we have just tried to find out many classes of many graphs whose chromatic number, local antimagic chromatic number is equal to this one. So one example is that same thing we have done this way. Another one we have taken as a, so this is a classes of the graphs we have taken here. So here we have taken the graph G. So we started and in using induction on the I. So I varies from here 1 to k. And then we take here I minus 1. And then we use the same join operation with the k and kt complement. Kt complement. And then we found that and a new graph here G I. And then start finding out the chromatic number and local antimagic chromatic number of that one. So this is the constructions we have given. And after that, we try to find out some classes of graphs. For example, if you take a cycles, okay. So if you take a cycle here, C3, this is a friendship graph, we know that one. This is a friendship graph. And we know that its chromatic number is 3. Local antimagic chromatic number is also the same in this case. Then we have taken a arbitrarily. So we have taken another graph. This is nothing but one edge common. This we have taken. Okay. So this is the way we have taken that one. So where cycles are there of different lengths, but one edge is common, like this. Okay. And then we started labeling the edges like this, 1, 2, 3. Then here 4, 5, 6. So in this case, you can see the vertices with this are going to get the same colors. Only these two are going to get a different colors. So this is a graph whose chromatic number is 3 and local antimagic chromatic number is also 3. Then we have started with the, actually I was trying to find out a CN1, CN2, like that T cycles I'm going to consider. And with one edge common. Here N1, N2, N3, Nt will be of any length. Okay. So initially we are getting the difficulties here, but finally we found when we are taking this case, first we tried to find out the equal length first. So suppose we have a graph of this type here, same length actually, with one vertex common, one edge common. Okay. In this case, we are able to succeed that one because if you label the edges in such a way that these colors and these colors are the same, these colors and these colors are the same, these colors and these colors are the same. So two colors and then 1 3 here. Then 2 colors will be different here. So we are able to succeed with the 5 colors. But in this case, the graph is two colorable only, 3 colorable, but local antimagic chromatic number is more than that one. And then we started with there's a one Lau, I think has given us something like that, Garland graph. He was defining that one. So if you take the graph like this, where degree 4 vertices are not adjacent. If you take any 2 degree 4 vertices, they are not adjacent. They said that it is a Garland graph. Okay, in this case also we are able to find out the local antimagic chromatic number. So these are some results we are getting. Now I think we have a limited time. How much I have, madam? Didn't count, okay. So, okay, then we thought that in 2018, when Professor Armugam is, I was discussing with sir and he was explaining the local antimagic chromatic number, all those things. Then onwards, we have started. then we say that why not we label the vertices and calculate the weight in the same manner. So if you label the vertices 1 to n and calculate the weight of the vertex as a usual vertex weight, which are in the neighborhood of n. And if we have take any adjacent vertices, if you have a different weights, we say that it is a local distance anti-magic coloring. Okay, because this vertex weights are going to give you the proper vertex coloring, and if f is satisfying this property, we say that local distance anti-magic coloring, it is a vertex version. Okay, so this name we have given, and we found some results on that one, but we just say if there is a graph which do not admit a local distance anti-magic leveling, then we just put a notation here that chi LD will be infinity. Okay, chi LD will be infinity, but we found that almost all graphs are having that property. So we are just going to try to see, otherwise we put a conjecture on that one. So we calculated the local distance anti-magic chromatic number of paths, cycles, wheel. It is very large actually. If you see that bounds, this is up to 6 and 7 here. Okay. And in this case, if you take a cycle with corona product with the Km complement, it is also locally distance anti-magic with the, since we have n here and m here, so we just put here this cycle is 6 here, so 6 plus n we are going to get using the magic rectangle set. We are able to find out the bound. Then we started with the union. So if you take the local distance anti-magic of the friendship graph, we got a 2n plus 1. Okay, we got a 2n plus 1. That number, it's a very big number. And if you take the union of that friendship graph, we got a equality here in both cases as a 2n plus r. So, and for complete graph, it is in the local edge version, it is also n. Here also it is n. Then this is a for complete multipartite graph M1, M2, MR is locally distance anti-magic with the local distance anti-magic chromatic number is R here. So this is a, there are some graphs for which chi LD will be also same as a chi of that graph. Okay, so it is interesting to search, find out all such graphs for which chi LD will be also same as a chi of that graph. So for these two cases, we are able to find out that one. Then here we have the complete, this is a star, which is 2, which is a part of this one. So there is nothing to worry about that one. Okay, so here we are just going to take the, sorry. Ln I am going to denote because here we have a K1n. We know that it is a local anti-magic distance anti-magic chromatic number is 2. So what will happen if I are just going to subdivide that one? Okay, if I'm going to subdivide, the local anti-magic chromatic number is going to increase here. So insert subdivision means the inserting the vertex in between the edges. Okay, so that is a way. In this case, we are able to find out if you subdivide, the local distance anti-magic chromatic number is going to increase drastically. And then we take the star. So here we have a tree. This is a tree, we are going to say that one. What is this graph actually? We take a path. Okay, so here central is a path, and then we are attaching the star and this one like this, something like that. Okay, so this graph we say that it is a like this. So this graph we say that it is a S1, S2, Sn, K. If there is a path, and each vertex we are going to attach the K1, Kn1, K1, N1, K1, N2, K1, Nk, then this is also distance anti-magic, locally distance anti-magic, and this is going to be happen like it will be lying between K and 2K. Okay. Now our job is to narrow the gap, and we are not able to find out such any constructions which will narrow this gap. It is very big actually, K to 2K actually. It is very big number range. And caterpillar, if I'm just going to take here, each vertex I'm going to put here k pendant to edges. Instead of that, k, n1, n2, nk, we are just going to put this way. So we are going to get this bound. So these are some results we are able to obtain. And still there are many classes are not explored. So we have explored for the path, cycle, star, caterpillar, corona products of graphs, bipartite graphs, multipartite graphs. And we found that certain graphs for which chi-LD is same as a chi of G and chi-LA is same as chi of G. But still, we need to know that if that is one problem is still open, we are trying to find out. So suppose you are going to give any number, can I construct a graph whose chi-LD is that number? That is a problem we are working, but not succeeded properly. Okay, so these are some conclusion. So in this case, and some references, I am going to use this one. So this is a paper where sir has posed a lot of problems. And this is a uniqueness, as I told you that. Magic constant is always unique, and this is a one thesis where in 2020 he just finished that one, and these are some results I quoted from this one, and this is the latest one, 2021 thesis. I have taken that work from there. I hope that I have finished in time. Thank you. Any questions?
Thank you very much. Are there some questions? Any questions, please?
Yes, sir. Yes, sir.
So
For smaller values of exact value, yes. In general, it is a bound, but equality is we are for some small classes of paths, we are able to get exact values. Yes, yes. Only bounds is there.
Some other questions? So if no, thank you very much again.
Oh, thank you. Okay.
Thank you very
Thank
much.
you very
for
much.
that. Thank you. Now I would like to introduce our next speaker. Our next speaker is Dr. Jay Bagga. I think that all of you know him. He was born in India and now he is working as a professor in the Department of Computer Science, Ball State University, Indiana, USA. He received his MS and PhD in mathematics from Purdue University. And he also received MS in computer science from Ball State University. His research interest is in the following fields: formal methods in software development and model, checking electronic voting systems, graph theory and graph algorithms, applications of bioinformatics and Bayesian network educational software on mobile platforms. He was awarded several awards, and he published more than 20 papers. His talk will be with collaboration with Professor Lowell Wayne Beinecke. He's professor of graph theory at Purdue University, Fort Wayne. Professor Beinecke is known for his elegant characterization of line graphs in the term of non-forbidden graph configurations. Professor Beinecke has taught mathematics at Purdue University, Fort Wayne since 1965. He received BS from Purdue University and MS from the University of Michigan. And he was a PhD advisor. His PhD advisor was Frank Harari. So now I would like to invite Jay Baga to give the nice talk. Thank you.
Thank you. You are able to show him on the screen, my presenter. Are you good? Well, thank you. Good afternoon. So I'm being joined by Mr. Lol Beinecke. This is a co-presentation with him. And soon we'll be hearing from him and seeing him, I guess, on the screen. He's already joined the Zoom presentation, I assume. Okay. Right. So, but his video is off. Does he need to turn it on? Oh, there he is. Yes. Hello, Lol.
Hello.
Your audio is off, Lol. I think you need to unmute.
I think I did.
Yes, we can hear you now. So yes, thank you. So on behalf of Professor Lol Beinecke and myself, I would like to start by thanking the hosts for this excellent conference and great organization. And it's been a pleasure working with you, all of you, and especially Dr. Rajesh Singh and Dr. Dipakshi Sharma, who've been here since the very beginning, working very hard with all of you others, all the nice work that you're doing in putting together this great conference. So we're really thankful for that. And so I'm here to thank you in person. I'm sure Lol is going to join me, thanking you from thousands of miles away. He's in Fort Wayne, Indiana, and it's around 4 a.m. On Thursday morning, 10 and a half hours behind this time. And he's up and he's awake, I see. So he'll be joining us here. So if we could go to our first slide, please. So which are the buttons? Okay, all right. All right, so here is an overview of our presentation. After some basic definitions and introduction, we will go into generalizations of line graphs. This is a talk about new directions in line graphs and line diagrams. And then we'll talk about one generalization that we've done in some detail, but there's still lots of interesting questions of similar generalizations for diagrams. So we'll talk about superline graphs and superline diagrams. Then we'll also talk about the line completion number of some of these superline graphs. And then we will look at some examples of superline diagrams of index 2, and then finish up with some other new directions in the area of line graphs and line diagrams. So recently, back in 2021, actually, Lowell and I published this book, Line Graphs and Line Diagrams by Springer. And this is, I would say, quite a comprehensive account of the state of the art in this. But since this book was published in 21 by Springer, a lot more has happened already. So new directions and new research is happening all the time. And we will refer to this book a few times in our presentation. So as has already been mentioned in some other talks already in this conference, the idea of line graphs has already been mentioned. So the concept of line graphs is quite simple actually. So if you are given a graph and you take two adjacent edges in the graph, E and F, then the line graph transformation takes those two edges and makes them into vertices in the line graph. And if the two edges are adjacent in the original graph, then those two are adjacent in the line graph. So that's why we use this color scheme. So our blue and red edges are in the original graph, and they become blue and red vertices in the line graph, and they are adjacent. So look at this example. Here we have a graph G with four edges A, B, C, and D, and that's the line graph. So notice that this A, B, and C, that's K13, that's a star, K13, and that turns into a triangle because you have three edges. A BCD is a triangle, which also turns to a triangle. So K13 has line graph, a triangle, and K3 also has the same line graph, and they are special. And Lowell will talk about that a little bit more when we do characterizations. So line graphs, the concept has been around for a long time. In fact, the line graphs first appeared in a paper by Whitney back in 1933, when he talked about edge isomorphisms. And as part of that work, he was able to show that the two graphs which are non-isomorphic but have isomorphic line graphs are K13 and K3, which is what you saw here. And so that's an interesting result, but then there's a lot more that happens beyond that. And then 10 years after that, in 1943, Krauss gave what's called the Krauss decomposition characterization of line graphs. And in a minute, Lowell will talk a little more about that. And that's a decomposition in terms of complete graphs, which have certain special properties. So since then, of course, one wants to know, when is a graph a line graph? So do you know, do we know how to recognize a line graph and such? And there have been algorithms for that too. So with this basic introduction of line graphs, the line graph transformation took off from there. This is a very active area of research with hundreds of papers that have appeared, and you'll find a good list of references in the book that I mentioned. So the characterization of line graphs was a big step in this area. And so now I'm going to ask Lowell to talk a little bit about the characterization of line graphs. Lowell?
Okay, the beginning of the characterizations had to do with the subgraphs, and that will come up, I think, in the theorem. But then a second characterization has to do with calling a triangle in a graph odd if some vertex of G is adjacent to an odd number of vertices of the triangle, as it says here. And it's called even otherwise. Next.
Next slide, please. I'll move it to the next one.
And so we have here the three main characterizations for a line graph. There's the Krauss one, which was mentioned, where the edges can be partitioned into complete subgraphs in a particular way, as it says here, that no vertex is in more than two of the subgraphs. And then Van Ruy and Wells looked at this idea of odd triangles, and the characterization is that you can't have two odd triangles forming a K4 minus an edge, that is, two triangles put together and both being odd. And then I was fortunate to look at that and find that there are 9 graphs that are forbidden as line graphs, basically. And that's the next slide. And these are the 9 line forbidden graphs. They have at most 6 vertices, and you can get the idea from the pictures, so that it's a nice, I think, set of forbidden graphs for line graphs. And then there are variations on this, but you'll have to look at other sources or our book to see variations of when you can have these and not. But I think it's really nice. And then we're going to look at digraphs, and directed graphs are in many ways very similar to graphs, but when it comes to line digraphs, the results are very different. And this is part of what makes it interesting, I think. So the line digraph of a digraph, and we assume that there's at least one arc, so we have a directed edge or arc. And so you must have them going in a sequence where the end of one is the beginning of the next, as the blue and red shows in Jay's picture here. And that's the line digraph operation. Next there. And so what we have in this picture, just to illustrate it, are the 6 possible ways of having 2 arcs in a connected digraph. We do allow loops some of the time, at least in this discussion, as well as reverse arcs. We could also have multiple ones, but we want to keep it under too much complication, and so we won't be doing that, at least not deliberately much. So here are then the line digraphs of the 2 arc graphs, and I think that shows the various features, and the red and blue illustrates what's going on there too. Next. So there are various things, and we don't have all of these here, but again, you can get the sources. We could do multi-digraphs, we could do loop-free, or we could do what it generally goes by the name of digraphs, where you don't have loops or multiple arcs in the same direction. And this is in chapter 2 of our book. Next. So now I want to look at the characterizations of line digraphs, and rather than grouping them all together, I'm looking at them individually as 3 different kinds of characterizations that we have. So I'm going to start with this particular digraph, and we formed the line digraph and you can check that, I hope at least, that this is the correct line digraph of that particular digraph. But what more can we say about it? Next. So this on the left is the line digraph, and on the right, I've kind of broken things up so that the vertices get split a little bit, but the arcs are analogous to what we have on the left. And if you look carefully at that picture, you can see that there's a kind of pattern. If we look at the bottom, we see that we've got 3 vertices, obviously, with 2 arcs, and they both go away from one vertex. And then to the right of that, something similar with they both come in. But note that they do not have any arrows, one following the other, in the usual pattern of a line digraph. And then the top part, well, that's got the similar pattern. If we take and look at the right 2 vertices, then we see that we've got a take K22 with the middle arcs, but then we've got that loop, and in fact, we've got a K23 by taking the arc in both of the in and out sorts of ideas here. So that gives us the characterization as an illustration here. And so we move on to the first characterization of the line digraphs, and that now we've got two pictures here that show this sort of idea of a complete, in a sense, bipartite graph with all the arrows in one direction, with the understanding that the loop serves double purpose. And so those are the sorts of oriented complete bipartite digraphs that we use that notation for here. A and B on the first were for the numbers, the sets on the right and left, and then we have it in parentheses later for the other one. So now we've got those things to talk about, and moving on to the next, writing it out in detail, a digraph and its set of arcs is a line digraph if and only if the vertices has a pair of special subpartitions for which we have this group of complete bipartite oriented sets of vertices, well, oriented arcs in the digraph. And my professor, Frank Harari, and his former student, who wrote a book on the directed graphs, the first book, I think, but it was in social work, not in mathematics. But there we have a very nice result, which is analogous to the partition that we had for Krauss in the graph case. Next. Now, there's something called the Huchen condition. Huchen was a Belgian mathematician and says that if we've got three arcs with that pattern that you can see there, then you must have the fourth for it to be a line digraph. That is, that's the condition that we have here. And this is a picture of the three black arcs that if we have those, then we must have the red arc as well. And that's then the picture of Huchen condition. Next. And that really is the second characterization that we have of line digraphs. That is, if you never have the three black ones without the red, the Huchen condition. So a very nice characterization. Next. Now we are looking again at the same picture that we had before at the line digraph on the right. And then what we are doing is forming the adjacency matrix of the line digraph. And so if I had the numbers up there, you would see it more clearly, but take my word for it. We have the first vertex in the picture that I'm using is the one down in the kind of middle of the left side of the line digraph. And it's got, no, it's the one at the top. I did change this. It's the one at the top with the loop. So we've got a 1 there and so on. So that's the line digraph matrix, adjacency matrix. And the property that it has is, next, that if you have 2 rows of that matrix, and we could go back and look at it, but you can check that, either the rows are identical or they are orthogonal, meaning that if you took the product of them in the usual kind of sense, then they would be zero or orthogonal. And the same applies to the columns. So we have kind of a pair of characterizations there, but really two versions of the same thing. So that's the third characterization of line digraphs. And then there have been lots of variations, like whether there are loops or not. And we could discuss some further of those, but I think I'll terminate this part of it and turn it back to Professor Baga.
Oh, thank you, Lowell. So you already saw in the characterization description that Lowell talked about, you saw the distinct properties or differences between graphs and digraphs, whereas the characterization of graphs was given in terms of those three conditions. Digraphs get more complicated and you get different characterizations of digraphs. And that theme kind of permeates all of this discussion throughout the line graphs, that line digraphs behave quite differently. And now that has also happened with generalizations. The area of line graphs is so rich in literature. There have been so much that's been done. And among that is many generalizations of line graphs that have also been proposed, and a lot of work has been done. And we also have looked at some generalizations ourselves, which is what we'll talk about next. So one of the generalizations that we found quite interesting, and it led to a lot of results, is the superline graph idea. So in the line graph, you take one edge at a time. So the vertices are individual edges. Now others have generalized it in different ways. Our generalization of superline diagrams is that we take sets of edges of the original graph G, but we take the same number of edges. So those become the vertices. So take a number R and then look at all the R vertices of R edges of G. Those become the vertices of what we call the superline graph LRG. And then we say that two of these vertices are adjacent if some edge in S is adjacent to some edge in T, where that adjacency comes from the original graph. Let's quickly look at a simple example here. Here's a graph G with 4 edges, A, B, C, D. And we are going to look at the superline graph of index 2. So 4 choose 2 being 6, there'll be 6 vertices. And we label them as AC, AB, AD, BD, and so on. But notice that they are not ordered. They should be sets. So that's a set containing the edges A and C. So we use a simpler notation. So it's really the set of 2 edges. So now AC is adjacent to AB because let's say A is adjacent to B in this. So that adjacent and so on. So you can define the adjacency. So you begin to see many adjacencies in the line graph of index 2. Well, the nice thing is that you can do it for any index. You don't have to just stay with 2. You could do an index 3, 4, and so on. And so in the next slide, we see what happens when you look at different indices from 1 to Q, because if Q is the number of edges in the graph, you can go all the way up to Q. So given a graph with P edges, you can create a natural sequence of these superline graphs, L1G, L2G, so on. And by the way, notice that the index 1, you are taking sets of 1 edge, you see. So that's exactly the line graph. So that's why this is a generalization of line graphs. And then you go all the way to LP, that is, there's only one set, so that's K1, ending in the trivial graph. So now it's not difficult to show that LIG is complete, then so is LI plus 1G. If at some index, the superline graph becomes complete, that means given any 2 sets of I edges, then clearly that's true for the next one. So since that's true, there is a least value L for which LIG is complete, and that is called the line completion number. In other words, we are looking to see in the sequence of superline graphs, when does that graph become complete? And that's the line completion number. Now we can do the same for digraphs, and we consider digraphs without loops. And now we define the LRD, just like we define LRG. We can define LRG with the same idea of adjacency that we saw for line diagrams. And then clearly L1D is the same as the line graph of D. So that gives you another sequence. Notice that in our definition, we do not allow loops, and it does not allow that. So let's look at an example here where we'll look at the sequence of these superline graphs. So starting with this digraph D, we look at index 1, which is L1 of D, which is same as the line graph of D. And you see that this is the line graph of D. Now, as you move to the index 2, you get L2 of D, and suddenly you have many more arcs because of all the adjacency that those arcs provide. And of course, 1, 2, 3, 4, 5, 6, there are pairs of edges, two sets of arcs, I should say, L2D. And then, but this is not complete in the sense of a complete diagram. Whereas L3 of D, which has now 4 edges, vertices, because 4 choose 3, and now you see that this is complete. There are arcs in each direction. So at this stage, it has become complete. L4 of D, of course, is a single node, which is also complete. That's a trivial diagram or trivial graph in this sense. So we can talk about the superline digraph concept and the line completion number. Now, as I said earlier, a lot more is known about superline graphs and not quite about superline diagrams. So that's there are some open questions and interesting new directions that we would like people to look at. So again, as I said before, in the case of superline diagrams, we have these simple observations that, of course, Lm of D, when M is the total number of all the arcs, is K1, and the line completion number of the digraph is the least R for which LRD is complete. Clearly, you can easily check that the line completion number of D is 1 if and only if D is either a path, a directed path, or a 2 cycle, which means 2 arcs in the diagram. Now, if you look at the superline graphs of index 2, we have many properties. This is a very rich class of graphs. We have looked at degrees, paths, cycles, and line completion numbers of these graphs. Excuse me. For example, we have shown that if G has at most one isolated edge, then in fact L2 of G is vertex pancyclic. So you can see a lot more of these kinds of properties in our book. But in contrast to that, superline graphs of index 2 are largely unexplored. So this entire set of superline graph idea for at least index 2 is still unexplored. And this is where I think there's quite a few open problems, interesting questions that we would like to look at. So now, in order to do that, we've been exploring some small diagrams. And I'm going to ask Lowell to come in again and talk about those.
Yes, as Jay said, this is a new work, and we are finding it very enjoyable, but we've only done it for little digraphs, I mean. And so we are challenging people to join us in analyzing these, perhaps some people who are more computer science oriented than I am, as far as getting some of these done, not by hand, but by computer. We might look at those, but let's look at some of these here. So to follow up on what Jay said before, we have starting off with just the superline digraph of index 1, which is the line digraph, and then we have that disconnected digraph. And next we have where we define it, and I've put it into more words here, which explain what you're looking at when you're making the line digraph of index 2, the superline digraph. We define it as having, as Professor Baga said, all of the n choose 2 pairs of the n arcs of D. So that's you've got then a set of 2 of these, and I'm just having the I less than J and K less than L to show how many there are. Then there is an arc from one vertex, and here I've jumped to just having the subscripts 1 and 2, one vertex to another vertex if one of the B's has the same vertex as one of the C's of the other vertex. So you get the direction. So I think we have another picture here. So if we have the transitive triple with now switching to unsubscripted letters, A arrow B arrow C and A arrow C, then we get the same graph again, the same digraph, since A arrow B. And that's the sort of thing we're looking at and seeing what happens as things go on. But we're only looking at things with about 3 edges, 3 arcs here that we're dealing with. It's showing, I think, that it's 4 in the morning or 5 in the morning by now here in Fort Wayne. So if I'm speaking a little tiredly, please bear with me. Anyhow, we put some natural restrictions on digraphs for this by looking at the numbers, and the notation that we use is type NM, where here we're looking at really 3-3 and 4-3 for our illustrations here. So moving on. So the transitive triple, which we just had before, is isomorphic to what we had, but that's specific to this small case, I believe. But then if we go to the cyclic triple, then we have the complete bipartite, the complete digraph on the arcs, every vertex to the others, remembering that we don't have loops in this case. And the next one then is the third possibility, which we called a balloon for lack of a better name, but we see that it has the property of getting the complete digraph again. And if we notice, I didn't put the opposite one because when you have digraphs that are converses of one another, a lot of the same properties hold. So the fourth one would have been essentially the same as this third one. But then we moved on to trees and then oriented them. So the first we had was the path of length 3, and we show its superline graph of index 2. And carrying on, we then have the other orientation of a path in the undirected case, which is shown here in the picture. And we have a different picture for that. But again, effectively, if you had the arrows going in the opposite direction, you end up with the same idea. But then if we have the vertex of degree 3 in our little tree, then we get essentially the same, except the arrows are going in the opposite direction. So that's what we have for the trees. And the next. So that's where we stop with that discussion, but I would like to again say, if you're interested in this, let Professor Baga or me know, and we'll see what we can put together. So Professor Baga, now the line completion number of graphs.
Thank you, Meineke. So again, you saw the same theme come through. We have a good handle on the superline graphs of index 2 and higher, but for superline digraphs, there's quite a few unexplored questions here that would like, perhaps some of you are interested in joining us in that research. So now let's move back to line completion number. So we have bounds on the line completion number. If you recall, we defined the line completion number is the smallest R for which the superline graph of index R becomes complete. And so we have this, and this actually can be generalized to graph with C components. This is a connected graph, but we also have a result for a more general result for disconnected graphs with C components. This has turned out to be a very interesting problem, is to determine the line completion number of certain well-known families of graphs. Some of these come by quite easily. So when we started looking at line completion numbers of graphs, we looked at complete graphs, we looked at paths, fans, wheels, windmills. I won't define these, but you can look in the literature for those, and even generalized cubes. So we were able to find, and with others, and others have contributed to this, line completion numbers. The general idea is to find a bound, find two graphs within the given graph, which are edge disjoint, so that the graph is, the superline graph is not complete yet, but in the next case, in the next index, it becomes complete. So Tapadia and Dr. Bafare proved this result about hypercubes, and they found the line completion number of hypercubes. And also grid graphs by another group of researchers from India that we have in our book is given. There are several cases, PS cross PT or the grid graph, the product of two paths. Now in all that list, if you will notice this list that we had, this one and this one and this one class of graphs that was missing is the complete bipartite graph, KRS. What is the line completion number of complete bipartite graph? Now it has turned out to be a very interesting problem, and the full problem is still open. A lot of work has been done in this already, and there's a paper that I'll mention, but it's not completely solved yet. So that's another problem that we would like all of you, hopefully you get interested in looking at this. So in other words, to find the line completion number of the complete bipartite graph, you want to split the graph into two sets so that the number of edges in the smaller part is as large as possible. So you take the complete bipartite graph, you break it into two edge disjoint sets where the smaller one is as large, and that gives you. Now it's easy to see what happens if R and S are both even. And that's, we have done that. But in general, it turns out to be a number theory problem, really. So if, in other words, if you are given two integers R and S, what is the maximum value of A, B, C, D, where A plus C is R and B plus D is S? You take all partitions of R and S in that sense of two numbers. So you want to minimize overall products A, B, and C, D. That is what we are looking for. So in a paper that was published in 2016, we did some work on this, and we found the line completion number for quite a few cases of the complete bipartite graph. And we wrote a tool, a software tool, to help us with the search of this. But that goes only so far. But that tool was helpful in giving us a lot of empirical data, and that data then helped us prove these results. So as I said before, if R and S are both even, then you just take half and half. Then it's easy to prove that the complete bipartite number comes through. But if not both are even, things get a little more challenging, a little more interesting. And you can see the formulas get more complicated. So if S is odd, we assume that S is bigger than or equal to R in this. And so if S is odd, R is odd. And so I won't go through the details of these formulas, but these are the ones that we proved. But that's not the complete story yet. There's more cases to be done. So there's quite a bit left undone in this problem of finding the line completion number of KRS. But even though we haven't completed this problem, and we hope some of you will get interested and pick up this problem, we went on to the next case, the tripartite graphs and others, to look at those. So again, in tripartite graphs, you are trying to find partitions, and in multipartite graph case, you're trying to find partitions. So for example, if you take this complete tripartite graph K345, it has 12 vertices and 47 edges. And we are looking for this partition into two parts, where the smaller part has as many edges as possible. So I'll show you an example in a diagram. So look at this. And so here you find the partition into two. So this K345 is split into K132 and K213. And it turns out that that's the partition we need for line completion number in this case. So we found some results here also for KRST, and we assume that R is less than or equal to S less than or equal to T. So if R, S, and T are all even, then we found this. So the beta value is what we call where the partition is. So one more than that becomes the line completion number. So that's known. And then for some other cases, we found, sorry, moved there too fast. So then we found that beta of 2k plus 1, 2k, when they're all odd but all equal, we know the answer too. But now we have several conjectures. Some of these we proved. And again, we extended our tool that we wrote for the bipartite graph. We extended it to tripartite graphs. And that data was helpful again in proving some of these. But quite a few of these conjectures are still open. So the bipartite problem is open in general, so is the tripartite. And so there's quite a few conjectures. And so is the multipartite, of course, that gets in hardened. So it'll be interesting to extend some of these results to complete n-partite graph. And we invite you to take a look at that if you are interested. Now, let us look at digraphs, complete line completion numbers of digraphs. So the open problem here is, like we showed you all the classes of graphs for which line completion numbers are known. Not much is known. This area is largely unexplored. So we'd like to find the line completion number of digraphs for several well-known classes of graphs, for example, tournaments or transitive tournaments, even and others, and see what we can do, or other kinds of digraphs. Lowell mentioned, Dr. Puspainike mentioned some of those digraphs earlier. Now let's move to another new direction in line graph, and I just have a couple more left that I'll talk about. One is looking at degrees in line graphs. Very little is known about this, and I invite you to look at our book and see what's known about what kind of properties do the degrees have in line graphs, degrees of vertices. So of course, it's clear that the degree of an edge E is the sum of the degrees of its two endpoints minus 2 in the line graph, right? So if E is the edge VW, then that's the degree. And then these results are easy to see. And of course, the line graph, if the graph has n vertices and m edges, then from that formula, it's easy to see that the line graph has m vertices and 1/2 sigma degree V square minus m edges. That follows directly from this. So what is known about degrees in line graphs is a couple of special cases. One is regular graphs, a deregular line graph of order m. So we know what the degree conditions, degrees should be. And I'll not go through the details of this in the interest of time. That's one special case. And the other special case is a sequence of positive integers d1 through dm, where the last degree is m minus 1, the highest one. Then that is line graphical, this sequence, if and only if the sequence has these conditions. So these results have been around for some time, but somehow no one has looked at this. So that's really an open problem of determining. And then, of course, one goes on to digraphs and else, but this in itself is an interesting problem to look at. So there are some papers by Brualdi and others on degrees or out degrees, like in digraphs, and I invite you to look at those. So this paper, which appeared back in 2011 by Brualdi and all, talks about all exponents of matrices, tournaments, and their line diagrams. So it's a very nice paper. And then one could look at other kinds of open questions that we have described here. Now, the last part of this talk, I want to now bring in yet another new direction. And do we have time? I'll just take 5 more minutes. And that is the connection between line graphs and graceful labeling. Now, graceful labeling has been mentioned in many presentations throughout this conference from the very first day. Quite a few of the presenters, invited speakers, talked about graceful labeling. So there is the definition of graceful labeling, and I won't repeat that. By now, you've seen this definition quite a few times. And of course, the well-known conjecture is the graceful tree conjecture, which says that all trees are graceful. Then there's also a similar conjecture about cycles and unicyclic graphs. Of course, we know which cycles are graceful. That was the result from Rosa. And in fact, there's some result on Eulerian graphs. So Rosa showed that cycles Cn are graceful if and only if n is congruent to 0 or 3 mod 4. Now, if you look at unicyclic graphs which are not cycles, then there is this conjecture of Szynski, which is still open, 1984 conjecture. All unicyclic graphs that are not cycles. And there's a lot of work has been done here. And so far, all the unicyclic graphs, these classes of graphs that have been shown to be graceful. So then I came across a paper in looking for if somebody had done any connection, looked at any connections between line graphs and graceful. I came across a paper back from 2002 by M. Murugan, and they studied graphs such that G and its line graph are both graceful. All right, and they call these graphs bigraceful graphs. So bigraceful means that G is graceful as well as L of G is graceful. and Murugan proved that paths are of course, because line graphs of paths are paths. Line graphs of cycles are the same cycles. So for n equals 0. And if you take K1 n less than equal to 5, that's the line graph is the complete graph. Up to 4, they are known to be graceful. So those are the easy results, right? These are the easy results. But then unicyclic graphs C4 with 2 non-trivial disjoint paths of the same length attached to any 2 adjacent vertices of C4. So then Murugan showed that these graphs are graceful as well as their line graphs are graceful. And then they also looked at some wheels. So therefore, I think this theory really needs, one needs to look at this new direction of classes of graphs, connections between the gracefulness of the graph and the gracefulness of the line graph. So you could ask these questions. Find all classes of graphs such that both G and LG are graceful. Or find those classes of graphs that neither G nor the line graph is graceful. find those classes where G is graceful, but LG is not. And finally, G is not graceful, but LG is graceful, line graph. So you have these 4 cases that are interpreted. We think we have some simple examples in some of these, and some. What I would really be interested in is finding classes of graphs and get some insight into what makes a graph and its line graph have this property, or both not have this property. So that's the kind of interesting new direction that we would like to throw out there for people to look at. So one of my PhD students, Pambi Max, and I, we proved, we shown that there is this unicyclic graph, a cycle of length n, and then you attach 2 paths, P sub t and P sub s, paths of t and s vertices, and then just path of 1 vertex. So you can, and for certain values of n, we've shown that this is graceful and its line graph is also graceful. So this one is bi-graceful. So we have some progress in this area where we have some unicyclic graphs which are bi-graceful. And so that brings us to a summary of the presentation. So we talked about line convolution numbers, of course, quite a few open problems, especially in the area of digraphs. Properties of superline graphs of index 2, really explore those. Explore connections between line graphs and graceful labelings. And of course, look at degree sequences of line graphs and line diagrams. With that, I'll end, unless Lowell, you have something to add to that.
No, I think you've done well there.
Thank you.
I would like to thank both our speakers for very nice talk. Are there any questions? Solutions?
Good afternoon, sir.
Good afternoon.
Sir, I would like to know how much progress has been done in sign graphs in whatever you have said, sir.
How much progress in line graphs?
Signed.
There is, in fact, there is, and I'll refer you to Professor Tarkeshwar Singh and others, but in our book, there is a chapter on sign graphs, line graphs of sign graphs. So chapter 16, Lowell, I don't know if I am saying the right number. There is a chapter, so there is some work that's been done.
So
I don't have those in my head at this point, but there is work there, yes.
So in signed line graphs, I've seen some work. Yeah, Professor Beneke has some work.
Yes.
But the super line sign graphs.
Yes.
Like how much has been done?
Yeah, so there is literature there, and I can refer you to those. We can connect after the talk, and I can show you where those references are.
Thank you, sir.
You're welcome. Yes. Let me ask, Lowell, did you have anything else to add to what we said on the signed graphs?
I don't think so, but I do want to thank the person who gave us the question there.
Yes.
I think that was nice. Yeah.
Thank you.
So line graphs are very nice graphs because they admit forbidden subgraph prediction given by Nikkei.
Yeah.
And then it can be recognized in polynomial time. Efficient algorithms are there.
Yes.
And many NP-hard problem also admits polynomial time solution.
Yes.
Restricted to this.
Right.
So what about similar kind of things are available for line digraphs?
Yes, in fact, there are recognition algorithms for line graphs and also for line diagraph.
But forbidden subgraph?
Forbidden subgraph, no. Because, yeah, I mean, after all, it's big O n to the 6, right? Because of the number of words.
Okay.
So you can actually do a brute force search on the graph to see if it's a line graph through the forbidden subgraph conjecture. But that takes a big O n to the 6. But actually, linear algorithms are known for recognizing line graphs, and similar small polynomial degree algorithms are known for line digraphs also.
No, but line digraphs, you have forbidden subgraph characterization?
Well, Lowell, do you want to handle that question?
I'm not sure that I have anything to say right now. have to,
So the question was, is there a forbidden subgraph characterization for digraph?
Line diagram.
yes, there is.
There is.
Yeah.
And so Lowell covered those three characterizations. Professor Beinecke talked about those three. One of those, if you go in details, and that's also covered. So there is a small list of digraphs, which in some special cases of oriented digraphs, for example, yes, there are. Yes.
Yeah, and if that person sends me a note, I can send pictures of those digraphs.
Professor Panda will be happy to send you those pictures. And they are in our book too, some of those. Yes. Yes. Thank you. Thank you, Lowell. Other questions?
No other question? So if no, so I would like to thank Jim Baga and Mr. Beinecke again. Thank you very much.
Thank you very much.
Good afternoon. The organizers asked me to announce 10-minute break, so we will see us soon.
Dear students, dear participants, we'll come back in 10 minutes sharp, and there will be another session by Dr. Deepa Sinha, and then we'll wind up. So please be here in 10 minutes. Thank you.
University Delhi. She received her PhD in applied mathematics in 2007 under the guidance of Professor Mukti Acharya. She is very active researcher. She published more than 120 research papers, and she is also very active as a teacher. She has guided many students, and today I would like to invite her to present her talk. Please.
Thank you so much. Hello. So, good evening, everybody. I would like to thank all the organizers for giving me the chance to speak in front of August guests of Delhi from abroad, and I'm really happy to see their faces. All my known colleagues and known co-workers, I really feel happy to see them in such kind of gathering. But it's only like my apology that I could not come for the first 2 days because I was with some other commitments. So with this, I again thank the organizers for giving me the chance to use the platform and give some of my findings in the area of graph theory. So today I'll be talking on encryption and decryption using sign graphs. So graph is a mathematical way of representing the concept of network. This talk has been organized as follows. It will be starting with the introduction, then encryption and decryption of sign graphs using RSA algorithm, and then encryption and decryption using sign graph transformation. So I think the second part, sign graph transformation, maybe it will be done online. So I will be today presenting encryption and decryption of sign graphs using RSA algorithm. So it is mainly intended to introduce definitions, most of the basic terminologies, notations required to understand the result reported in the talk. Also, it gives the glimpse of major problem tackled of directions of research followed. Can it be enlarged? Oh, I'm so sorry. I will just. So graph, everybody knows, is made up of vertices or nodes and lines called edges that connect them. It will be depending on the model. So model will require the entities. Entities will be the nodes or vertices in mathematical language, and however they are connected, they will be joined by the Jordan curve that is called edge or arcs, whatever the context may be. Formally, a graph is a discrete structure formed by a vertex V whose elements are called vertices and the collection E of elements called edges, each of which is a 2 subset. As we see here, this is a graph. So these are the entities 1, 2, 3, 4, 5, and then how they are connected according to the model. So they are F, B, A, C, D, G, and all. These are the links. Then an algorithm is a procedure or formula for solving a problem. A word derives from the name of the mathematician Muhammad ibn Musa al-Khwarizmi, who was a part of the royal court in Baghdad. In mathematics and computer science, an algorithm is a step-by-step procedure for calculations. Algorithms are used for calculation, data processing, and automated reasoning. So there are different ways to store graphs in a computer system. The data structure used depends on both the graph structure and the algorithm used for manipulating the graph. Theoretically, one can distinguish between the list and the matrix structures. But in concrete application, the best structure is often a combination of both list and matrix structure. List structures are often preferred for the sparse graph because they require smaller memory, and on the other hand, matrix structures provide faster access for some applications, but the memory required will be bit larger. So adjacency matrix, we all know, is in case of the sine graph, which is denoted by capital S with n vertices v1, v2, vn, and having no parallel edges, will be represented as A is equal to under braces Aij, where Aij will be taking the values -1, 0, and 1 for ij varying from 1 to n. So n is the number of vertices. So that is how Aij will be, that means Aij means Vi joined to Vj. If it will be joined to Vj, then it will be 1. If by a positive line 1, by a negative line -1, and if it is not joined, then it will be equal to 0. So that is what. So secret communications have been needed by military officers and diplomats since ancient times. In today's age, where the internet, mobile phones, and computer technology are widely used in almost every sphere of life, the need to keep important information secure and confidential is utmost important. Over time, as data security continues to evolve, there are continuously new ways to break the confidential communication are being day-to-day discovered. Cryptography is the study of changing restricted information into coded data so that can be secured, so that can securely arrive at its end without spillage. It was fundamentally used for at the time of war. Old time cryptography, it revisits after 2000 years. Modern cryptography is highly connected with discrete mathematics. Many cryptographic algorithms are directly based on mathematical results. So these are I'm talking about what are what is the concept which I'm going to use in my talk when I present the finding. Cryptography is a scientific and practical activity associated with developing of cryptographic security, facilities of information, and also with argumentation of the cryptographic resistance. And cryptanalysis is a scientific and practical activity of analysis of cryptographic algorithms with the goal to obtain estimations of their cryptographic resistance. So cryptology is the concept of combining both cryptography and cryptanalysis. And encryption and decryption, the process to transform the original message into a coded format is called the encryption, and the reverse process will be called as a decryption. And plain text and ciphertext. Plain text is a non-encrypted message with the help of a specified key. Plain text information is encoded or encrypted to generate ciphertext in any encryption technique. So this is what I'm going to talk about by using RSA algorithm. See, we have been, the traditional method is generally Fourier transform, and then affine transformation and all that. So now as it has been told in my previous slide, that day to day several other discoveries are being done, because encryption and decryptions have become very important in many areas. Okay, so whenever you want to lock something, or you never want to conceal something, or you want to make it confidential, it becomes very important. And going by the traditional methods, by making slight changes into that, why not we use of traditional method and start making that popular? And then if that becomes obsolete, one can discover other methodology. So here in this lecture, the main focus is on the development of a new cryptography mechanism for secure data transmission and retrieval by using a sign graph, its adjacency matrix, and the RSA algorithm. This concept is implemented on network of any cities or any place, you know, when suppose the cities are joined and you want to, they are joined by the road or whatever, and to that road or to that link between the two cities, you want to place something, and you want to, and it has to be placed confidentially, not to be known to others. Then how would you transfer this to, and if you want to transfer this to the internet, and you don't want that this gets vulnerable and to attack and all that, so you have to use certain measures so that it gets so that it remains confidential. So in 1970, so we are here trying to do with the RSA algorithm. In 1977, an algorithm was described by Ron Rivest, Adi Shamir, and Leonard Adleman, and was first publicly known example of secure practical algorithm that could be used to encrypt secret messages without somehow establishing a secret key beforehand. As a public key cryptography system, RSA algorithm calls on intended recipient of an encrypted message to create a public and private key. He publishes the public key which anyone can use to encrypt the message, that is encode the message, to code the message to him, and keep private key secret. The RSA algorithm public-private key pair generation is based on a difficulty of factoring large integers. One can see in this Nisha S and Farik M. They have written a review in that everything comes in a descriptive manner. So RSA algorithm for generating public key, select two prime numbers. So this is now the process. Main process now begins here. So select two prime numbers P and Q and calculate n is equal to P star Q. Those P prime numbers must be bit larger number. Choose the number E such that, sorry. Choose the number E such that E must be first of all an integer. Then it must be relatively prime to n. What is n? N is P into Q. That is GCD of En must be equal to 1. And E must be strictly greater than 1 and less than the torsion function phi n. So then the public key will be denoted by bracket En. For generating private key, calculate the value of phi n, that is torsion function. Phi n will be equal to P minus 1 into Q minus 1. P and Q are the prime numbers that we have already selected. Calculate the value of D such that D cross E reduced phi n must be equal to, modulo phi n must be equal to 1. Then the private key will be equal to Dn. So public key is En and the private key is Dn. The public and private keys are used for encryption and decryption respectively. So based on concept of sign graph, adding more security to network, an effective mechanism is designed for encryption and decryption of matrices through sign graph by RSA algorithm. So this is the proposed. So let the adjacency matrix of the sign graph S. So with n vertices v1, v2, vn and no parallel edges be represented as Aij, as already told to you. The adjacency matrix related to sign graph S is symmetric. So adjacency matrix always remains symmetric for the graph. So for the sign graph also. Due to this characterization of matrix, the upper triangular matrix and the lower triangular matrix will be similar. And because we will not be considering the parallel edges and loops, so the diagonal elements will be equal to 0. So the upper triangular matrix is denoted by capital U and the lower triangular matrix is denoted by capital L. So U will be same as L or L transpose. Then, so adjacency matrix is like this. A is equal to this. Upper triangular or lower triangular matrix is enough to recognize the adjacency matrix. So let us consider only the upper triangular matrix for encryption and decryption process. So calling, write all the elements of the, so now we are getting into the process. So write all the elements of the upper triangular matrix. Write all the elements of the upper triangular matrix as a number starting from the last row, and for each row the direction of writing should be right to left. The number of digits in this number is, so upper triangular elements will be how much? If it is n cross n matrix, the number in the number of elements in upper triangular matrix will be n square, that is the total number, minus n divided by 2. N is the diagonal element. So where n is equal to number of vertices in the sign graph S. Now every minus 1 is considered itself as a decimal number. So once I will be explaining this with the example also. So when, see, because the adjacency matrix will be containing minus 1 also. So minus, wherever it comes minus 1, you take it minus 1, because here they are asking you to write it as a chain of numbers. Okay. By following this process. So whenever it comes minus 1 will be taken as decimal number. In between, you will be getting the sequence of binary numbers 0 and 1. Binary sequence 0 and 1. So you convert that sequence again into decimal. That has to be converted into a decimal number that I will now every minus 1 itself is considered as a decimal number. Rest, which is a string of only 0 and 1 separated by minus 1, are considered as binary numbers. In the next step, what we do to those binary numbers, we add 1 in the beginning, 1 in the beginning and 1 at the end, and convert those newly obtained binary numbers into the decimal number. And minus 1 will be 1 decimal. So there can be many decimal numbers, but then their number will be lesser than R, where R is the total number. Number of digits in this will be n square minus n by 2. Okay. So this will be somewhere up to k, where k will be less than equal to R. So for encryption, the values of D1, D2 and DK. The values of D1, D2, DK are encrypted by applying RSA algorithm to get the encrypted numbers. So, and now see, D1, D2, DK we have obtained. Now we will encrypt it to alpha 1, alpha 2, alpha k. And this ciphertext is sent to the receiver, who can derive the original matrix by applying some sense by reverse process. So for decryption, after receiving the encrypted values, that is ciphertext, it is decrypted to get the values of D1, D2, DK, k varying from 1 to R. Further, every DI except for minus 1 is converted to binary numbers to construct the upper triangular matrix U. So this is the whole process that we are following. So the order of constructing the matrix is row-wise. Here the first rightmost digit represents the last entry of the top row to last row. By continuing this process, the upper triangular matrix will be derived. The lower triangular matrix can be constructed automatically by taking the transpose of the upper triangular matrix, and the adjacency matrix of the given sign graph is produced by putting them together. So now that you are again back to the graph. So, so this is the algorithm, how you write. This is the pseudo code. And then, so these are the steps that we will be following. And then for encryption as well as decryption. So So let us consider some map, some graph. Okay, so let me consider this as a this is as a sine graph, where these are the positive edges receiving the value 1, 1, 1. These edges will be receiving the value 1, and this edge will be receiving the value -1, as we can see. I'm sorry. As we can see here. This is for the same map, this is the graph, and which is the cities are denoted by the vertices V1, V2, Vn, and then there is only one negative edge that is connecting V1 to V5. Whenever there is a dotted edge, the weight given to that edge is -1, otherwise the weights are +1. And when there is no edge, like there is no edge between V3 and V1, the weight will be 0, obviously. Okay? Or we will take it as a 0. So the adjacency matrix will be, you write the row wise and column wise V1, V2, Vn. So where Vi's and Vi to Vi will always be equal to 0. So they are 0. Diagonal elements are 0. And V1 to V2 must be connected in the graph. So it is equal to 1. V1 to V5 is -1 because they were connected by dotted lines. So it is -1. And see, however, whatever is the upper triangular matrix, same is the lower triangular matrix, because it will be matrix will always be symmetric in this case in the graph. So the number of elements in the given upper triangular matrix will be n square minus n by 2, which will be in this example, because it was 7, n was equal to 7. So it is 7 square minus 7 by 2, that is 21. So 21 numbers. So applying encryption process that I have been telling, all the elements of the given upper triangular matrix will be represented as this. See what? How do we how to put that? Okay. See this. How we will start from here. 1. Okay. This is the upper triangular matrix. Okay. 1. Then 0, 0. Then 0, 0, 1. Then 0, 0, 1, 0. Then 0, 0, 0, 0, 1, and then 0, 1, -1, 0, 0, 1. This is how you are going to write the sequence. Okay. So this is how you got the sequence. This is the sequence you have got like this. Okay. So this -1, there can be more -1, but this -1 is separating these two strings of. This is 0, 0, 1, and this is another string. So to convert these two binary number strings into decimal number, and -1 is itself considered as a decimal number. So D1 is considered as this. You have to prefix it by 1, and then here also you have to put 1 in the end. Okay, and D2 is -1, D3 is 0, 0, 1. So 0, 0, 1 prefixed by 1, and then at the end also 1. So convert this into binary numbers. So this is being converted into binary number, which convert this binary number into decimal number, sorry, and this will be equal to this. And D3 is another this thing which has been converted into decimal number, which is 19. So we have 3 decimal number. 397835 -1 and 19 for the particular example that we have chosen. Therefore, for implementing encryption and decryption using RSA algorithm, we have 3 values: D1, D2, and D3. Yes? 5 minutes. Okay. Just so input the values of. So we have chosen 2 prime numbers: 397401. Compute n. That was P cross Q, which is equal to this. Compute phi n, which is P -1, Q -1. All that was already told to you while explaining the process. So which comes out equal to this. Choose E, which is the number which has to be greater than 1, less than phi n. It has to be integer. So we can choose E as 23. Compute D such that this was also told earlier. So D, we get D, D is coming out to be 6887. So public key is En, which is equal to 23, and this, that is En. and private key is DN, which is 6887 by the process used, and then encryption with public key. So encryption with public key. So alpha 1, alpha 2, alpha 3 can be calculated like this. So these are the values, encrypted values. Now alpha 1 is this, alpha 2, alpha 3. So for decryption, use public key, the 6887, and this public key we remember if you DN. Okay. So input the value of alpha 1, alpha 2, and alpha 3. So D1 will be equal to alpha 1 raised to power D modulo n, which is equal to this much. D2 will take the value this much. D3 will take the value this much. And then after converting all the positive integers into binary numbers and the reverse process, the upper triangular matrix U is received. And after transpose of U, the lower triangular matrix L can be received, and U plus L will be totally giving you the adjacency matrix constructed. Thus, encryption and decryption. So here in between, certain logs can also be used to make it not vulnerable to attack. Okay. So this is the process, and these are the references that has been used.
Thank you very much for that. So we have time for 2 questions, maybe short questions. Any questions? Yes.
Hello. Yeah, ma'am. If instead say if you use ECC elliptical curve algorithm, means does this process add extra security in your algorithm? Means suppose instead of RSA, I use elliptical curve cryptography.
See, I cannot say that this has extra this thing, but I can say that if you have more and more number of this thing, so if you are applying certain graph theoretical methods,
yeah.
I am not comparing this with any other, but then if you have more and more methods, at least people will not be able to see, because the general trend is by using that whatever you are talking about, and then Fourier series and affine and all that. So, and with the same lady picture, they just start with that. All the literature survey shows that. But then, if you have some different methods, and if you are going by some different methods, you will be not. It will not be easy to attack. That's what.
Thank you.
We have time for 1 more question.
Madam, I wanted to know, like, the graph you have taken is not balanced actually. So, I mean, is there any interpretation of the balance, unbalanced,
Here, see, in my online talk, I will be using the transformation. See, it has balance has got nothing to do. But if you want to encode it with balance and certain other sign graph properties, you can. So it has nothing to do with balance or anything. But if you want to use for your purpose, for your model, you can.
will there be any value addition, like?
It will depend how you are using. It may.
Thank you.
Okay, so last question.
But I want to point out that if you want to encrypt the sign graph
using RS and yeah.
So I can now use the normal RSA and just adjacency matrix without going through this. I can apply the RSA. That also will be an encryption decryption, right? So what is the advantage that you are getting by doing
I was just trying to tell, advantage is that I was just trying to tell that if there is some network, in that network, if you want to connect it with network, of course you will be going to the matrix only. Whenever you are taking network, that means here in my process, graph means network, network means matrix. So matrix, say you get some, see again, that's what my first answer was to that student, that you have to arrive to so many other different methods so that it may not be easily captured. That's all.
So thank you very much again for nice talk.
My pleasure. Thank you.
Please wait for a moment.
I thank Professor Andrea and Professor Deepa Sinha for a wonderful talk. Now we'll be having the valedictory session. Just a 2-minute gap. Everyone is requested to be seated, and then we'll start with the valedictory. thieves, nor it can be taken by kings. It cannot be divided amongst brothers, nor it has any weight. If spent, it always keeps on growing. The wealth of knowledge is the most superior wealth of all. Knowledge is what has brought us all here. A very good evening to all. It is the final welcome before we come to the end of these 3 days of extravaganza of International Conference on Graphs, Networks, and Combinatorics. I request the dignitaries, Professor S.P. Agarwal, Professor Alfred Kamenetz, and Professor Rajesh Singh to join us on the dais. Please give a huge round of applause. We'll start with our convener of the conference, Dr. Rajesh Singh. I request him to please come here and give the report of the conference.
Thank you, Dr. Dipakshi. Honorable Chief Guest, Professor Anfred, Aerodynamic Professor S.P. Agarwal, Principal Ramanujan College, all the eminent international and national speakers, more than 450 participants, paper presenters and contributors joining this conference from online as well as offline mode, faculty members and dear students. Good evening and a warm welcome to all of you in this valedictory session of the International Conference on Graphs, Networks, and Combinatorics. The conference is being organized by the Department of Mathematics, Ramanujan College. Being the convener of this conference, I am here to present a brief report about the conference. Before proceeding with the report, I would first like to thank our chief guest, Professor Anfred, for agreeing to grace this occasion. And I would also like to thank all our resource persons for their enlightening and enriching presentations. It is said that an hour spent in the company of a scholar is worth reading 100 books. Here we have spent around 72 hours in the company of 19 internationally renowned experts from all over the world. Definitely, every participant must be having a feeling of accomplishment and acquisition of knowledge. I would also like to sincerely extend my heartfelt thanks to all the participants of this conference. Throughout these 3 days, I have been so much impressed by the eagerness shown by the participants in all the sessions. The enthusiasm they bring fills us with energy and joy. I also take this opportunity to thank and congratulate our principal, Professor S.P. Agarwal, for the successful completion of this event. Kudos to the principal, sir, for giving us the full liberty to invite resource persons from diverse backgrounds, both geographically as well as academically. Sir has been a guiding light throughout this endeavor. I also take this, I must also thank all the sponsors of the conference, SERB, SERB, DRDO, UGC, Indian Oil Corporation, ONGC, and Punjab National Bank for their generosity in providing financial help to the conference for its smooth conduct. At the end of these days, it gives me immense pleasure to present the report of the proceeding that went during the last 3 days. A total of 455 participants from different colleges and universities across the world joined this conference. In particular, we had 150 participants from Tamil Nadu, 60 participants from Karnataka, 47 participants from Kerala, 33 from Gujarat, 20 from Uttar Pradesh, 19 from Maharashtra, and there were also 6 participants from outside India. As per the feedback received from the participants of the conference, most of the invited resource persons were highly resourceful, eloquent, and articulate in putting across their viewpoints. The presentations made by most of the invited resource persons were rich in content, where they not only shared their knowledge, but also their wisdom and their lifetime experiences, giving real life examples of the efforts they had put in their own areas of expertise. Over the last 3 days, the conference witnessed 9 international and 10 national speakers, 450 plus participants, with more than 150 attending in the offline mode. There were more than 250 paper presentations in the conference, spread over 30 parallel sessions for paper presentation. 12 were offline and 18 were online. We also had more than 125 outstation participants. The conference proceedings will be published in the form of special issue of the 4 Web of Science and Scopus Index journals. I'm quite sure that this conference must have been a stimulating and invigorating experience for all the participants and will in turn immensely benefit them with their research. To my understanding, any program is successful if the participants are able to grasp most of the knowledge, skills, and ideas imparted to them. Looking at the feedback received from the participants from the past week and also the interactions that we had during the live sessions, I believe this conference is able to achieve its goal of being an igniting tool for quality research in mathematics. I wish all the participants had a great learning experience at the conference and will apply the same to enhance their research. Once again, Happy New Year to everyone. Thank you. Dr. Dipakshi, please take over.
Thank you so much, sir. Now I request pillar of our institution and our inspiration, Principal Professor S.P. Agarwal, for their address.
Thank you, Dipakshi. Once again, good evening and welcome. Well, let's say 3 days, you can say very concentrating, exhaustive, and maybe fruitful exercise by all our young faculty members. I hope Dr. Rajesh just read the report. The volume spoke that it must be a good exercise. On behalf of Ramanujan College, I'm thankful to each one of you, especially to the participants, because they are the valuable asset to us and the students and everyone. All the eminent international and national speakers, today's guest, Professor Arnfield Chemnitz from Germany. As Rajesh said, 450 participants, paper presenters, our other speakers from all over the country in India. Once again, all our faculty members, students, welcome to this valedictory session. Friends, I will not take much time because it's already 5 and you are looking forward to go home. The main thing I would say that our purpose for this conference was very simple. The vision of the college is to discover, empower, transform, building a better world. And another important thing was that the NEP 2020, I'm reading a quote, mathematics and mathematical thinking will be essential for India's future and India's leadership role in the numerous upcoming fields and professions that will involve artificial intelligence, machine learning, and data science. Therefore, it is highly imperative of any higher education institute to organize and disseminate mathematical knowledge, skills through conferences, workshops, and seminars on regular basis. I am delighted that the Department of Mathematics, to some extent, has gone into that direction. And probably all of you must be benefited. Of course, the institution is getting benefited. Even I feel all our speakers and eminent people who are in the field are also being benefited through dissemination. And our purpose that there should be a interdisciplinary research, there should be consultancy, there should be IPR and patents out of this conference. So that should also be achieved, because our satisfaction will be much more if something of that kind will happen. So that is our key takeaway from here that we should taking into account the NEP 2020, that we should encourage interdisciplinary research, and mathematicians' role is the highest, as I said in the beginning also, because we have to teach this area to everyone, because no research is possible, whether it is science, social science, medical science, today, even in medical science. And the topic you have chosen, the graph and the networking, probably is the best application in any of these fields. So that field, if we can use further, probably things can be much, much better. In the end, I really thank from bottom of my heart and from side of this institution, all our international speakers. We tried our best to make their stay comfortable, but there might be shortcomings. So I really take everything on me, not on my young faculty, that if something is, not taken care of or something can be done better, please suggest us so that next time we will take care. We are really thankful to all our national speakers, especially some of them are very close and friend to me, and a guiding force to this institution. Again, I'm naming Professor Armugam, Professor Purnima Gupta, who has been guiding these people to get into this area and to organize such a conference. I'm also thankful to my personal friend, Professor Hegde, who is always, eager and always give time to this institution. I have seen him all 3 days here and listening very patiently and doing his work meticulously. So once again, friends, I also congratulate my young team to do a wonderful job in organizing this kind of conference, especially Dr. Rajesh, Dipakshi, and all young friends, Tripathi ji. Everyone needs, appreciation, all our supporting staff, all our housekeeping staff, all our IT staff, everyone needs appreciation, because this kind of work, when done in a smaller institution, is really a very satisfying. And with your feedbacks, with your suggestions, we will ensure that this kind of extravaganza and this kind of conferences should happen every year, in this institution. We have no problem, absolutely. Of course, we could not do in last 2 years because of the COVID, but we will continue to do these things so that we can exchange knowledge of each other. Thank you very much.
Thank you so much, sir, for your inspiring words. Associating with wise and knowledgeable person adds to the prestige of people. Today also, we have our special guest, Professor Arnfred Kemnitz, who is wise, knowledgeable, and a distinguished speaker. Sir, we are lucky to have you here today. Please grace us with a few words.
Yeah, hello. Hello. It's a big honor for me that I have the opportunity to thank the organizers in the name of all participants, especially of the invited speakers, of the national and international invited speakers, to thank the organizers for a very, very great job. That they welcome us and give us the opportunity to listen to interesting talks during the last 3 days. Especially, I would like to thank for the great hospitality they give to us during these days. Here, during the conference, we had some 20 national and international invited lectures, and we had, as far as I know, more than 250 paper presentations, and I was really very impressed about this enormous encouragement, especially of the younger students and of the younger participants giving their lectures. And I think the organizers did really a great job in recruiting strong partners, which made it possible that such an excellent event could be held. And the importance of graph theory, which interacts with discrete mathematics and theoretical computer science, is growing up since a long time, above all because of its numerous applications in science and technology. And a large bandwidth of interesting topics of this area have been presented at this international conference by the participants. And I'm sure that this conference will be an interesting, or was an interesting event, such that we all profit from scientific and also personal exchange between all of us, between the participants. And therefore, I would like to express my very deep gratitude to all the organizers to make this possible. Thank you very much.
Thank you, sir, for your presence and your words. Now we request some of the speakers to please give their feedbacks. Please, anyone, please. Professor Andrea?
I will just say a few words. I would like to thank again for inviting me. For me, it was somehow complicated to get visa, but I am very happy that at the end I received visa and that I could spend here beautiful 3 days. Thank you very much for everything.
Professor Laszlo?
So last time I was in India was a conference 5 years ago, and unfortunately during COVID, there was no conferences and no travel. And I'm looking forward for the future when I can attend great conferences like this again. Thank you.
Thank you, sir. Professor Katona?
I also want to thank you for the fantastic organization. I myself organized many conferences in Hungary, just to mention the second European Congress in Budapest. So I know how many errors you can commit, and congratulations, you were able to avoid them. So thank you very much for your kindness.
Thank you, sir. Professor Arumugam?
I'm extremely happy that this conference went done so perfectly that the meticulous and careful arrangements by the coordinators and the excellent support by the principal of the college that has made it a very memorable and nice event. I hope that we shall come together more often. Thank you very much.
Thank you, sir. Professor Kiki?
So I would like to thank the organizer, because this conference may be like the first conference that we attend in 2023, and it's going very well. So thank you very much.
Thank you, ma'am. Professor J. Bagga?
I would like to begin by thanking the organizer, especially Dr. Rajesh Singh, the convener, who that's how our interaction started. And since then, I've been very excited and very in great anticipation. And I must say that that was definitely met the expectation I had. One of the main features for me, a couple of main features. I have not been to Ramanujan College before. This is the first time, but I hope that it won't be the last time, that I would love to come back again and keep interacting with you. One. And the other one of the hallmarks of a successful conference is the networking, as Principal Agrawal mentioned, all the productive work that happens post-conference, after the conference. And I was so happy to see many participants who I have met off and on when I visit And they come to me and say, hey, we met at such and such conference, and this is what we are doing now. And so that's been very, very satisfying to me. And I think we have already started discussing some collaboration with some. And I think that is the best measure of the conference, is how much productivity happens after the conference with this networking. Thank you.
Thank you, sir. Professor Riva.
I would also like to thank the organizers for their work in organizing the conference, and also all the other people who were involved in the work here. And I am glad to say that I have heard some very interesting talks, not in just the invited sessions, but also in the contributed sessions. And I wish you success in continuing this. Thank you.
Thank you, ma'am. Professor Hegde.
Good evening, everyone. First and foremost, I'd like to say that there are no comments or complaints. There are only compliments. Okay. Sorry. I was associated with this event maybe almost starting from the beginning. I kept in touch with Professor Rajesh, and I used to ask, what is your expectation? So he was telling about 40 offline and some online. And I was asking him, if the number is more, do you have the alternative? He used to tell, yes, I have. But recently, when he told it is more than 125, I was shocked really. Because this is winter. Making arrangement in winter for accommodation is almost impossible task for 125 people. And he convinced me that it's possible. That is what shows the support which he has with him. I really wish that every principal would be like Professor Agarwal. When I asked him about the budget, and he told me, sir, money is not a problem, you go ahead with. So definitely, I'll tell you, even now, money is not a problem if you are sincere, serious, and put efforts. Money cannot be a problem. Only thing is, it's mindset of somebody that I may not get the money and all. Money is not a problem. If you are good, definitely you will get money. And I am really happy that even during valedictory, so many people are there. Normally in the conferences, only during inauguration, you can find people, but not during the valedictory. So that shows the interest of the participants as well as the speakers who are all there for all the 3 days. So normally in many conferences, you will not find that. The people will come, give their talk and leave. So that will not benefit the participants. If the speakers as well as participants both are there together, then only the purpose will be served. And with this, I hope we will meet again in Ramanujan Institute for some other conference. Thank you, sir.
Thank you, sir. Professor Deepa Sinha.
Last but not the least, I was able to make it for this conference. So I missed everything. But whatever I hear from all the speakers and the participants, I really feel that I would have been here, but my other commitments, I could not come. So it's only my apology, but I really missed everything. That's what I can only say right now. But I was updated about each little thing by Dr. Dipakshi, and it was going great. So, and also from Dr. Rajesh. So I wish very best to all the staff, all the faculty members who put in their efforts for such a nice conference. And as Professor Eva was saying, 5 years back, or he was saying that they were in South Asian University only for the conference, and Professor Katona, I think he was here 5 years ago for the conference. So most of them I met that time, and I wanted to meet them. So even though I was to skip my talk, I thought I will somehow make it for the valedictory so that I am able to see these people. So really great. And all the inspiration they get from Professor Agarwal. So I wish everybody very best for everything, and then may the coming conference that you organize maybe all maybe the big and great success for this college, and you become the brand name of Delhi University. Okay, thank you.
Thank you so much, ma'am. Now I request some of the participants to come forward and give feedback, suggestions. It's a voluntary effort. Yeah.
Hello, everyone. As a participants, I just to say thank you to the organizers, and apart from the efforts made by the organizing committee and the sponsors, I think the way the boys and girls who have worked for us throughout the 3 days, they need a round of applause, huge round of applause. So a huge shout out to the student team. Thank you.
So we request you to introduce yourself as well.
My name is Karan Odedra. I am from Gujarat University, Ahmedabad.
Thank you, sir. Participants, any suggestions for us? We will try to improve it next time. Dr. Manju?
Good evening to one and all. Actually, as Hegde sir said, our flight was at 3 p.m. So we are not supposed to be here for the valedictory function, but our flight got delayed, and hence we got a chance to attend the valedictory function. So thanks to AirAsia for that. First of all, the conference held, it was a very nice experience. All of us are attending an offline conference almost after 2 years. Personally, for me, I'm attending a conference offline outside Kerala for the first time after the COVID scenario. So happy about the conference. Just one comment I have to make. There were so many paper presentations. It would have been better if you give us the abstract of the papers, because we couldn't understand where the paper presentations are going on and what all things are being presented by the presenters. So that's the only suggestion that I have to make. Food and accommodation were excellent. The speakers were the excellent ones that we have obtained. And thank you all the participants. As everyone wished, let's meet again.
Thank you, ma'am. And the e-abstract book will be mailed to each and every participant after the conference concludes. Dr. Aarti? No, not yet. Anyone?
I have one more remark, that to organize a conference like this, it's an incomplete problem, and you have solved it in polynomial time. So the open question is settled. PH equal MP.
Thank you so much, sir.
Thank you so much, Principal Agarwal, and all the management people of Ramanujan College. It was a dream for us. I'm Sister Amali. I'm the only one nun in this conference, I think. And this is a great exposure from Tamil Nadu Auxilium College, and near Vellore VIT we are, and a very good experience. It was a dream, but I could express my sincere thanks for each one of you, especially for all the contributors as well as the management staff from convener as well as everyone. Everyone is so kind and the hospitality was great. I'm grateful to you all. We have 5,000 girls and in our campus, and I wish everyone have this experience coming out from the place, environment, and learn. This is very good experience, and especially really I'm express my sincere thanks from the bottom of our heart on behalf of our principal and our college members. Thanks for all the participants, and I could not say this can be extended all those things because each and everything with love and kindness you have achieved it. Great to Ramanujam College. Thanks.
Thank you so much, ma'am.
Hello, I'm Chitij Chhetri from Sikkim. First of all, I'd like to thank you for this wonderful opportunity to come participate in this and present our paper. I mean, I also work in a college, and then to come to a college that has this A++ grading, and then try to figure out what is there which we don't have, and then 3 days. I mean, I was also trying, but then the way things move here, like almost everybody in this college tried to make us comfortable, whether they're associated with this conference or not. The students, I mean, very rarely we find students such a wonderful, I mean, who can be so responsible, from the person who knocks at each and every door in our guest house to ensure that we take the breakfast on time, we board the bus on time, and while leaving from here, they are here to see that, okay, the last person has boarded the bus, and a student doing that. I mean, it's wonderful. So I mean, and I found that like many things work in unison. So I probably, so principal sir, I mean, all credits to you and then all. So, but having said that, coming to this conference part, so it was like, a wonderful expository exposition to us in this topic in the last 3 days. And we look forward to more such opportunities in the future. Thank you. Thank you so much.
Thank you, sir.
Good evening, everyone. My name is Radha Madhavi, and I have completed my PhD after 22 years of educational gap. So attending this conference is a very big thing for me, and it's a very pleasant experience, excellent arrangements and excellent talks I have attended. So I'm very happy. So I am thanking you all for giving me this opportunity to attend this conference and present my work. Thank you.
Thank you, ma'am.
I am Arun. I am from Kerala. I am about to start my research work. So it's personally my first experience in a conference. And just being with these persons who share the same passion about mathematics is just fascinating. And for that opportunity, thank you so much to the college. And these guys are just simple, unassuming. Their presence, their very presence actually radiates energy. So it's absolutely inspiring. Just to be here for 3 days means it's just inspiring. So I can't enumerate the positive compliments, but I, along with all these participants, would assure you one thing. If at all we get an opportunity to come back to this college, we'll not think twice. Thank you so much.
Thank you so much, sir. You're always welcome to visit college whenever you wish to. Thank you, everyone, for your suggestions and feedback. I now request Dr. Virender Kumar to deliver vote of thanks.
Thanks, Dr. Dipakshi. It all started with the suggestion from Professor Armugam and Professor Purnima Gupta. So when we had suggestion from the professors, we met Professor Agrawal, our principal, he just said, okay, go ahead. So these are the words for which we are waiting for. And whenever we are going to him for any work, he always used to say, okay, go ahead. So these words are really booster for us and inspiration for us to work hard and do better each and every time. So, offering vote of thanks for such a massive event is most important and difficult task, as I feel that no word can be sufficient to offer one's gratitude. On behalf of organizing committee, I, Dr. Virendra, offering my humble gratitude to our chief guest, Professor Anfred Chemnitz, Germany. He's associated with us for a long time, and he used to visit us and give lecture here a few times back also. Sir has kindly agreed upon and accepted our invitation and taken out time from his busy schedule to grace the session. Sir is very down to earth, as in every interaction we find there, and very helpful for all of us. Sir, having you here is a great honor for us. Thank you, sir, for sparing your valuable time with us. Thank you, sir. My thanks to the chairman of governing body, Ramanujan College, for his all-time support and motivation to utilize the platform in full capacity. Thanks to our dynamic and energetic principal, Professor Agrawal. Under his dynamic guidance, the college has achieved many milestones, and the college every day getting new pearls in the crown. Sir, your words, the personal success is one thing, but how organization and stakeholders are getting benefited is most important. Have always been focus point for us. Thank you, sir. Thank you for your guidance, encouragement, and keeping a strong belief in the strength of the Department of Mathematics. My heartfelt thanks to all resource persons across India and abroad who kindly agreed upon sharing their expert knowledge with the participant of the program. I'm happy to share that every expert whom we contacted for this conference kindly agreed upon to join it in either physical, that is offline form, or either online way. Now I would like to thank all international and national advisory members of the conference. Thanks to all participants from Pan India and abroad also. Without them, it would have not achieved this much success. So once I would like to request a big round of applause for all participants. Thanks to the organizing committee members, Mr. Pappu, in charge of the department, mathematics, Dr. Megha Agrawal, Mr. Rahul, Dr. Rajesh Singh, the convener of the conference, Dr. Deepakshi, co-convener of the conference, Mr. Deepak, Mr. Sanyam, Mr. Alok, Dr. Rajiv Nain, Dr. Prakhar Wadhwa. My thanks to the finance team, Mr. Anil, Mr. Sumit Suhag, Ms. Priyanka, Mr. Jagota ji, Mr. Rajesh ji, Mr. Prasant, Mr. Sanchit, and Mr. Akhil. Thanks to Mr. Dayanand ji, section officer, and Mr. Ram Prasad ji for their all-time help whenever we needed. Thanks to our technical team, Mr. Anil ji, Vinod ji, Ravi Vis ji, IT head Narendra Sharma ji, and entire IT department, because this program was online as well as offline, and each and every talk was going simultaneously offline and online. So it requires huge support from IT department. So they have done very good job and played very vital role in the successful conduct of this conference. Thanks to our technical team, Anil ji, Mr. Vinod ji, Ravi Vis ji, IT head. Thanks to our electrician, Sithilesh ji, housekeeping staff and guards, our gardeners, Mr. Santaram ji and Mr. Ashok ji. Our student volunteers have worked very hard and played very vital role in the successful conduct of this event. They worked so hard, even they used to stay here until 9 o'clock or 10 o'clock, some students. And even they used to go to receive in the night, late night or early morning to our guests. They have put lots of effort. Student volunteers under the leadership of Lara and Ashish Kashyap and other students also of all 3 years, first year, second year and third year. Thanks to all support given from logistics, facility, IGNU, Jamia Millia Islamia, Jamia Hamdard University also. They provided us the rooms and guest house for a stay or guests. Thanks to housekeeping staff and the lift operator, Mr. Sri Hariji. Special thanks to Dr. Sumit Nagpal, Department of Mathematics, University of Delhi, who have been in contact and always make suggestion for a successful conduct of this conference. Now, most important thing was the fund. So we got so much support from many agencies like SERB, UGC, DRDO, Indian Oil, ONGC, and PNB. And these funds were an encouragement for us to conduct such a massive program event with more than 450 participation. At the end, I would like to thank each and everyone whose name I forgot to pronounce, and those who are directly or indirectly are involved in this event. Thank you. Thank you so much, sir.
Thank you, sir. So with this, we have come to the end of 3 days of International Conference on Graphs, Networks, and Combinatorics. The time flied in the blink of an eye. I hope you all enjoyed and gained knowledge during these 3 days, as we love to organize these events. With a wish of happy, blissful journey ahead, I, Dr. Dipakshi Sharma, co-convener of the program, take your leave and wish you all the best from the organizing team and Ramanujan College. All the very best.
Congratulate this institute for getting the highest grade an education institution can get. They got
Thank you so much, sir. Thank you. There's a little announcement for all the participants. You can collect your certificates from outside. There are different counters. Alphabetically, the certificates are arranged, so you can take them from outside. Thank you all. Thank you for joining us.